Okay, hello everybody. So thank you for the examination board to accept the invitation to participate in this thesis defense. I'd like to thank you everyone, Professor Manuel Gil Ortega from the University of Seville, Professor Leonardo Torres from the Cal Poly in California, and also from UFMG. Also, I'd like to thank you, Professor Adriano Siqueira from São Carlos, Professor Ricardo Takahashi from the Department of Mathematics here in UFMG, and Professor Vitor Costas, my colleague here in the department, Belt, from the UFMG. And also I'd like to thank you, Sergio, Professor Sergio, from the Department of Aeronautics and University of Seville. He is advisor with me of Daniel. So I start this defense. This is the so now I ask to talk in Portuguese because this procedure should be conducted in Portuguese. Essa é a defesa de número 363, da defesa de tese de doutorado do programa de pós-graduação em Engenharia Elétrica da UFMG. O candidato ao título de doutor, Daniel Neri Cardoso, irá apresentar o seu trabalho intitulado Robust Control Framework in the Weighted Sublab Space. Ele foi orientado por mim, Guilherme Ganarrafo, do Departamento de Engenharia Eletrônica da UFMG, e pelo professor Sérgio Esteban Ronceiro, do Departamento de Mecânica dos Fluidos e Aeroespacial da Universidade de Sevilha, na Espanha. A banca é composta pelo professor Leonardo Antônio Borges Torres, da Cal Poly, na Califórnia, Estados Unidos, e também membro do PPGE. Pelo professor Ricardo Hiroshi Caldeira Takahashi, Departamento de Matemática da UFMG, pelo professor Adriano Almeida Gonçalves Siqueira, da Departamento de Engenharia Mecânica da USP São Carlos, e pelo professor Manuel Rio Ortega Linhares, da Departamento de Engenharia de Sistemas e Automática da Universidade de Sevilha, e pelo professor Vitor Costa da Silva Campos, do Departamento de Engenharia Eletrônica da UFMG. Então, nós iremos iniciar a defesa com a apresentação do Daniel, que deve ter em torno de 50 minutos. Né? Logo depois, nós faremos uma pausa, né, principalmente para o pessoal que está no Brasil, que pega bem o horário do almoço, e a gente retornará ao 12h30 para fazer a arguição do candidato, e passado a arguição, a gente passa a fase de deliberação da banca. Okay, so I was talking in Portuguese about the schedule. We start now with the presentation from Daniel. After you make a break for lunch from the people in Brazil until 12:30. It's about, I think, 5:30 in Seville and 8:30 in United States, in California. And after you come back to make the round of questions and evaluate the candidate. So Daniel, thank you for your work. So now you have your 50 minutes to present the thesis. Okay. Your time. Thank you.
Thank you. Good morning, everyone. Initially, I would like to thank the committee for accepting the invitation, and I also would like to thank my advisors, Guilherme Ganarrafo and Sérgio Esteban, that helped me during the development of this PhD thesis. This PhD thesis is called Robust Control Framework in the Weighted Sublab Space. I split this presentation in 6 topics. I will begin with an introduction to motivate the formulation of the nonlinear H2 and H-finch controllers in the weighted sublab space. Then I will present the formulation of the nonlinear double two and double infinity control with approximate solutions, the formulation of the nonlinear double two and double infinity controllers for mechanical systems, the formulation of the linear double infinity controller. Then I will employ these controllers in the case study of the Doutorado AV, and at the end I will conclude this work and present some future works. When designing controllers to attenuate disturbances, two usual approaches are the classic H2 and infinity control approaches. These controllers were originally formulated in the frequency domain. In this domain, the H2 controller seeks to minimize the energy of the disturbance with impulse response, while the H-infinity controller seeks to minimize the maximum gain given by the closed-loop system to a disturbance signal. Due to the need to deal with systems represented in the time domain, Doyle et al. Extended this control approach to multiple input, multiple output systems represented in the state space, and Van der Schaft formulated the H-infinity control approach for nonlinear systems using theory of dissipative systems. However, the H2 and H-infinity control approach present a drawback. They deal mostly with the aspects of the disturbance attenuation and provide little control over the transient behavior of the system. When it comes to the design of H2 and H-infinity controllers for mechanical systems, a pioneering work is Johansson that formulates the nonlinear H2 controller and proposes an analytical solution to the resulting Hamilton-Jacobi equation. Based in this particular solution, Chen et al. Formulated the nonlinear H-infinity controller and proposed a similar solution to the Hamilton-Jacobi equation. Regarding underactuated mechanical systems, the controller is usually formulated by exploring some characteristics of the mechanical system. In Siqueira and Terra, for example, they explore the passive-active degrees of freedom and have to design the controller consider the system has input coupling. However, the nonlinear H2 and H-infinity control approach for mechanical system also present drawbacks. In this case, besides the drawbacks of the nonlinear H2 and H-infinity controllers, the standard formulation of these controllers for mechanical system presents limitations in the way to weight the cost variable. Seeking to handle with those drawbacks, Aliu and Bocas proposes the redesign of the H2 and H-infinity controllers in the weighted Sobolev space. The weighted Sobolev space is the space of functions in LP whose generalized derivatives up to order m are also in the LP space. So is a subspace of the LP space, and in this kind of space, all the properties of the LP space are satisfied. This space have already been applied in the control area to design states observers, propose new kind of stability definitions. And the advantages in the approach proposed by Aliu and Bocas relates in the fact that in their approach, the energy of the cost variable and its time derivative are minimized in the optimal control problem. However, the approach proposed by Aliu and Bocas also presents drawbacks. For example, they do not allow waiving the influences of the cost variable and its time derivative in the cost functional, and they result in complex Hamilton-Jacobi equations to be solved. So, in order to handle with those drawbacks, this doctoral thesis formulates the nonlinear H2 and H-infinity controllers in the weighted Sobolev space. These new approaches are here called W2 and double infinity controllers. Especially is intended to formulate the nonlinear double two and double infinity controllers in the weighted Sobolev space via dynamic programming and propose a numerical algorithm to achieve the solution, a solution to the resulting Hamilton-Jacobi equations. Formulate the nonlinear double two and double infinity controllers for mechanical systems represented by the Euler-Lagrange equations and propose analytical solutions for fully actuated, reduced, underactuated, and underactuated mechanical systems with input coupling. Formulate the state and output feedback linear double infinity control problems via convex optimization with LMI constraints. and extend these control problems to take into account the time derivative of the disturbance. Besides, we demonstrate the efficiency of the double-two and double-infinity controllers via numerical experiments and perform comparison analysis with the classic H-infinity controller. And also, we employ these controllers in the case study of the Roto EV. So, in order to justify the formulation of the nonlinear H2 and H-infinity controllers in the weighted subological space, initially we highlight some interesting features of these controllers. To that, consider this nonlinear system where x is the state vector, tau is the input vector, and w is the disturbance vector. And consider two cost variables, the cost variable h, that's used to formulate the nonlinear H2 controller, and the cost variable z, that's used to formulate the nonlinear double-two controller. Regarding these cost functionals, the H2 control problem is posed as finding an optimal control law that minimizes the L2 norm of the cost variable h, while the double-two control problem is posed as finding an optimal control law that minimizes the weighted subological norm of the cost variable z. In the left side, we have the span cost functional of the H2 control problem, and in the right side, we have the expanded cost functional of the double-two control problem. Initially, we can see that the double-two control problem weights component-wise the output vector and its rate of change in the optimizing index. Besides that, as will be demonstrated in this work, the inclusion of the dynamics of the system into the cost functional by the double-two control problem provides a kind of anticipatory behavior to the closed-loop system. Therefore, the resulting controller provides an improved transient performance. In addition, in the double-two control problem, the control law is not required to belong to the L3 space, allowing the formulation for nonlinear systems in which the function f evaluated at the origin of the state space is different of 0. Since for such systems, it is necessary to keep injecting energy in the system to maintain it at the origin of the state space, so requiring control laws that are not in the L3 space. In the case of the H-infinity controller, the H-infinity control problem is posed as a min-max optimization problem, where we want to find an optimal control law that minimizes this cost functional for the worst case of the disturbance. The cost functional is posed considering the L2 norm of the cost variable h, and the double infinity control problem is posed as a min-max optimization problem, where we want to find an optimal control law that minimizes the weighted subological norm of the cost variable z for considering the worst case of the disturbance. And in this case, we can say that the aforementioned features of the double-two controller also holds for the double infinity one. Besides that, we have that the variable gamma have different meanings in each control problem. In the H-infinity control problem, the variable gamma is an upper bound for the energy induced by the disturbance on the output variable h, while in the double infinity control problem, the variable gamma is an upper bound for the energy induced by the disturbance on the cost variable z and its time derivative. So, in this topic of the presentation, I will formulate the nonlinear double-two and double infinity controllers in the weighted subological space via dynamic programming. It will be considered nonlinear autonomous systems. Besides that, it is proposed numerical algorithms to approximate solutions of the resulting Hamilton-Jacob equations. These controllers are synthesized for a two-wheeled self-balanced vehicle, and we perform comparison analysis with the classic H-infinity controller. So now we will consider autonomous systems given by this plant P1, where x is the state vector, u is an affine input vector, and z is the cost variable that's a function of the states. So the double-two control problem is posed as a minimization of the weighted subological norm of the cost variable z. In this doctoral thesis, we formulate this control problem via dynamic programming, from which we obtain this Hamiltonian, And by minimizing this Hamiltonian with respect to the control input, we obtain the expression for the optimal control law, and then the Hamilton-Jacob equation that must be solved to achieve the controller. In the case of the nonlinear double finch controller, the control problem is posed as a min-max optimization problem, taking into account the weighted subvolume norm of the cost variable z. And here we consider the point P2, where we are now considering the effects of the disturbances in the system. This control problem is again formulated via dynamic programming, from which we obtain this Hamiltonian. And the worst case, the optimal control law and the worst case of the disturbances are obtained by minimizing and maximizing this Hamiltonian with respect to these variables, which leads to these expressions for the worst case of the disturbances and the optimal control law. And then we obtain the Hamilton-Jacob equation that must be solved to achieve these controls. The Hamilton-Jacob equations resulting from the double two and double finch controllers are hard to solve analytically. Therefore, in this work, we propose numerical algorithms to approximate solutions of these Hamilton-Jacob equations. This is the numerical algorithm proposed to approximate a solution to the double two control problem. In this algorithm, we start with an initial stabilizing control law. And in this loop here, we perform successive Galeckian approximation in order to converge asymptotically to the solution of the problem. This is the algorithm proposed to approximate a solution to the nonlinear double infinity control problem. In this algorithm, we start with initial stabilizing control law and set the worst case of the disturbances equal to 0. And then we perform two loops. In the inner loop, we seek for the worst case of the disturbances for this initial stabilizing control law, and then we update the control law and seek again for the worst case of the disturbance. It can be demonstrated that this algorithm converges asymptotically to the solution of the problem. In order to verify the efficiency of these controllers, in this doctoral thesis, we perform numerical experiments with a two-wheeled self-balanced vehicle. The model of this vehicle are given by these Euler-Lagrange equations, where the vector of degrees of freedom are the angular position of the pendulum and the angular position of the wheels. And for the sake of comparison analysis, an H-finch controller was also designed, and all the controllers were tuned to achieve the same a similar settling time with respect to the angular position of the pendulum. And in order to perform the Galeckian approximation, it was used as basis functions, a full polynomial with degree 4. Here we have the results. Since the all the controllers were tuned to achieve a similar performance with respect to the settling time of the pendulum angular position, we can see that all the controllers achieved a similar performance with respect to the angular position of the pendulum, and also with respect to the time derivative, to the angular velocity of the pendulum. However, when we look to the time evolution of the wheel's velocity, we can see that the controllers formulated in the weighted subvolume space achieved a better performance. Here is the quantitative analysis of the results. And we can see here that since the controllers were tuned to achieve a similar performance with respect to the settling time, they achieved a similar performance with respect to the ISE index computed for the angular position of the pendulum and also to the angular velocity of the pendulum. However, when we look at the ISE index computed for the wheel velocity, we can see that the controllers formulated in the weighted subvolume space achieved an improved performance and with a similar control effort. In this topic of the presentation, I will formulate the nonlinear double two and double finch control approach for mechanical systems represented by the Euler-Lagrange equations. It is proposed analytical solutions of these Hamilton-Jacob equations for fully actuated and reduced underactuated mechanical systems, and also for underactuated mechanical systems with input coupling. Besides, it will be performed numerical experiments with a quadrilateral AV and a comparative analysis of these results with the classic nonlinear H-fin control. So now we will formulate the control problem considering mechanical systems represented by the Euler-Lagrange equations. And these first controllers are formulated for reduced and weighted mechanical system. To this, we consider that the rank of the input coping matrix is equal to any tau, and we choose any tau degrees of freedom to be called as controlled degrees of freedom, while the remaining degrees of freedom are called uncontrolled degrees of freedom. Then the system is manipulated and represented by the dynamics of the controlled degrees of freedom, where we assume that this matrix B bar here, the determinant of this matrix B bar here is different of 0. Therefore, this matrix is invertible. The objective of these controllers is to provide trajectory tracking of the controlled degrees of freedom, and it is assumed that the uncontrolled degrees of freedom have stable dynamics or are input to state stable with respect to Kc. Thus, they can be stabilized through an additional control strategy imposed on the time evolution of the controlled degrees of freedom. For the sake of designing the double-two controller for reduced underactivated mechanical system, initially the system is manipulated and represented in this standard form P3, where the state factor is given by the error of the controlled degrees of freedom, its time derivative, and its integral action, and the cost variable z is chosen in order to provide constant disturbance rejection. And similar to the previous controllers, the nonlinear double-two control problem is posed as a minimization of the weighted sublab norm of the cost variable z. And the control problem is formulated via dynamic programming, from which we obtain the Hamiltonian, the expression of the optimal control wall, and also the Hamilton-Jacob equation that must be solved. And in this control formulation, due to the particular selection of the cost variable, this Hamilton-Jacob equation is simplified, therefore allowing to propose a particular solution to this Hamilton-Jacob equation. Besides that, in this doctoral thesis, we present the corresponding stability analysis. In the case of the nonlinear double-finch controller for reduced underactivated mechanical system, the dynamics of the controlled degrees of freedom is again manipulated and written in terms of this standard form here, where now we take into account the effects of the disturbances in the system. And the control problem is posed as a min-max optimization problem, taking into account the weighted sublab norm of the cost variable z. The control problem is again formulated via dynamic programming, from where we obtain this Hamiltonian, the expression of the optimal control wall, the worst case of the disturbances, and also the Hamilton-Jacob equation. And in this case, we have that this term here in the worst case of the disturbances is equal to 0. Therefore, the double-two and double-finch controllers become equivalent. And the solution proposed to the Hamilton-Jacob equation of the double-two controller is also a solution of the double-finch controller. In order to verify the efficiency of these controllers, they were synthesized for a quadrilateral AV. The model of the quadrilateral AV is given by these Euler-Lagrange equations, where the vector of generalized degrees of freedom are the Euler angles that describe the orientation of the quadrilateral AV with respect to the inertial frame, and the position of the quadrilateral AV with respect to the inertial frame. The control inputs are the square of the angular velocity of the propellers, and for the sake of control design, it was selected as controlled degrees of freedom, the attitude and altitude dynamics of the quadrilateral AV. For comparison purpose, an H-fin controller is also synthesized and tuned to achieve the same IADU performance. Here we have the results of the numerical experiment, As can be seen at the beginning, the quadrot AV starts displaced from the desired trajectory and converges to it. And when the disturbances are applied to the system, we can see that the controllers formulated in the weighted solid space achieved a better disturbance attenuation with a less oscillatory behavior. This is the quantitative analysis of the results, and as I said, the controllers were tuned to achieve a similar performance with respect to the control effort, but when we compare the ISE performance index computed for the control degrees of freedom, we see that the controllers formulated in the weighted subwave space achieved an improved performance. In a second control approach proposed by this doctoral thesis for mechanical systems, we formulate the nonlinear double two and double finch controllers considering the entire underactuated mechanical systems. To this, initially we assume that the rank of the input coping matrix is equal to any tau, and now we choose any tau degrees of freedom to be called as controller degrees of freedom, while the remaining degrees of freedom are called stabilized degrees of freedom. And the control problem is formulated by assuming the system has input coupling. The objective now is to provide trajectory tracking of the controller degrees of freedom while the remaining ones are stabilized. In order to formulate the controller, the system is manipulated and represented in the state space, where the state vector is the arrow of the controller degrees of freedom, its time derivative and its integral action, and also the time derivative of the stabilized degrees of freedom. And the control inputs, it's written in terms of the generalized inputs. Besides that, we grow in the vector D here all the terms related to the force induced in the system by gravity and also the force necessary to perform the desired trajectory. And we assume that there exists a configuration of the stabilized degrees of freedom such that the projection of the disturbance vector and this vector D in the new space of the input coping matrix is equal to 0. Then the system is represented in this standard form P6, where now we consider two cost variables, the cost variable ZC and the cost variable ZS. These cost variables are chosen to provide tracking and constant disturbance projection to the control degrees of freedom while stabilizing the remaining ones. And the control problem, the double finch control problem, is posed as a min-max optimization problem, taking into account the weighted subwave norm of those two cost variables. This control problem is again formulated via dynamic programming, from where we obtain the Hamiltonian, the optimal control, and the worst case of disturbance, besides the Hamilton-Jacob equation that must be solved. And similarly to the previous case, in this case we have that this term here in the worst case of the disturbance is equal to 0. Therefore, the double two and double finch controls become equivalent. And in this doctoral thesis, we present a particular solution to this Hamilton-Jacob equation with the corresponding stability analysis. So, in order to verify the efficiency of this controller, it was also formulated for the quadrot AV. In this case, we considered as controller degrees of freedom the yaw angle and the position of the Doutorado AV, while the stabilized degrees of freedom are the roll and pitch angles. And for the sake of comparison analysis, an H-finch controller is also synthesized and tuned to achieve a similar EADU performance index. Here is the result of the experiment. As we can see, the quadrot AV starts displaced from the desired trajectory, and it is designated to track this H-shaped trajectory here. And we can see that both controllers achieved good performance. And here is the time evolution of the stabilized degrees of freedom, the disturbances applied to the system, and the norm of the projection of the of the disturbance vector and the vector D in the null space of the input coping matrix, where we can see that at the beginning and when the quadrilateral V is subject to external disturbances, the controller manipulates the stabilized degrees of freedom in order to provide an appropriate mapping using pseudo-inverse of the generalized inputs to the control inputs. Here is the quantitative analysis of the results, and we can see that both controllers were tuned to achieve a similar performance with respect to the EADU performance index, but when we compare the performance of the with respect to the ISE index computed for the controller degrees of freedom, we see that the controller formulated in the weighted subwave space achieved an improved performance. So, in this topic of the presentation, I will present the formulation of the state and output feedback linear double infinity controller via convex optimization problem with LMI constraints, the formulation of state and output feedback linear double infinity controller consider disturbance dynamics, the formulation of polyplacement constraints, and the extension of these controllers to handle with uncertain systems. So, in a first approach proposed by linear control to handle with linear systems, we design a state feedback linear double infinity controller. In this case, we assume a linear system where X is the state vector, U is the input vector, and W is this disturbance vector. And the matrices A, B, and D represents the dynamics of the linear system. And the control law is state feedback control law, where this matrix K here must be obtained by solving the optimization problem, and the cost variable is considered as equal to the states. The control problem is posed as a minimization of the double infinity index subject to these constraints, and this control problem is manipulated and with several manipulations, change of variables, and using the Shu complement, it is represented by this resulting convex optimization problem with LMI constraints. In a second approach proposed for linear systems, we consider that not all states of the systems are available for feedback. Therefore, we consider this output variable here, that's a linear combination of the states, and the control problem is formulated considered a dynamic controller, where XF is the states of the dynamic controller, the matrices AF, BF, CF, and DF are matrices that must be obtained by solving the optimization problem, and the control law is a linear combination of the states of the dynamic controller plus a linear combination of the output vector. The control problem is again posed as a minimization of the double infinity index, and with several manipulations result in this convex optimization problem with LMI constraints. In a third approach proposed for linear systems, we formulate this controller taking into account the weighted subwave norm of the disturbances. So in this case, we take into account the time derivative of the disturbances in the control design, and this controller is now we consider state feedback, and the time derivative of the disturbances are computed by means of a disturbance model, where this matrix AD, BD, and CD gives the dynamics of the disturbance of the disturbance model, and D is the state of the disturbance. V is an exogenous signal that excitates this disturbance. The control problem is again posed as a minimization of the double infinity index, which with several manipulations, change of variables, and using the Shu complement result in solving this convex optimization problem with LMI constraints. In a third approach proposed for linear system, in this doctoral thesis, we formulate the control problem considering the weighted subwave norm of the disturbances and also output feedback. In this case, we consider this output variable y, the model of the disturbances, and a dynamic controller. The control problem is posed again as a minimization of the double infinity index, where with several manipulations, change of variables, and using the Schur complement, we obtain this resulting convex optimization problem with LMI constraints. This doctoral thesis also formulated polyplacement constraints that allow to synthesize the double infinity controller with the closed loop poles allocated in a predefined region D of the complex plane. And we also demonstrate how to design the linear double infinity controller for uncertain system in which the system has an uncertain variable epsilon that belongs to a non-compact convex set. The results of the linear double infinity controller will be presented in the case study of the Tutu-Hauter. In this topic of the presentation, I will present a detailed modeling of the multi-body dynamics of the Tutu-Hauter. It will synthesize state and output feedback linear double infinity controllers for trajectory tracking of the Tutu-Hauter operating the helicopter flight mode. And also, we design a nonlinear double infinity controllers for trajectory tracking throughout the full flight envelope of the convertible plane Tutu-Hauter. So, the Tutu-Hauter is a kind of aircraft that can perform vertical takeoff and landing and hovering as helicopters and improved cruise flight with higher speeds and less energy consumption as aircraft. From the point of view of control, the challenge when dealing with this system is that the dynamics of the system change in each flight mode. In the helicopter flight mode, for example, the deflection of the control aerodynamic surfaces does not generate significant force, and the controller must guide the UAV using only the group of thrusters. While when transitioning and in cruise flight mode, the controller can take advantage of the deflection of the control aerodynamic surface in order to generate forces and moments that can be used to guide the UAV throughout the desired trajectory. Besides that, Tutu-Hauters are usually subject to disturbances from any sources, such as wind gusts, parametric uncertainties, and unmodeled dynamics, therefore requiring robust control laws to achieve acceptable performance. From the best knowledge of the presenter, the design of a single-layer nonlinear controller to handle with the multi-body dynamics of the Tutu-Hauter throughout the full flight envelope is an open field in the literature. The Tutu-Hauter aircraft used in this work is the Provant Emergência Tutu-Hauter. This UAV is composed by the fuselage, where the electronic components are assembled, wings that poses as control aerodynamic surface the deflection of the right and left ailerons, a V-tail that poses as control aerodynamic surface the deflection of the right and left rudder vehicle, and two groups of thrusters, one at each side of the aircraft, that is composed of several motors, an engine, and a propeller. In this doctoral thesis, the equations of motion of the Tutu-Hauter were obtained using the Euler-Lagrange formalism and written by the Euler-Lagrange equations, where the vector of degrees of freedom are the tilting angles of the servo motors, Euler angles that describe the orientation of the Tutu-Hauter with respect to a inertial frame, and the position of the Tutu-Hauter with respect to a inertial frame. And the control inputs are the angular velocity of the propellers, the torques applied by the servo motors, the deflection of the ailerons, and the deflection of the rudder vectors. The disturbances are the components of the environment wind speed given with respect to the inertial frame. So in order to compute the vector of generalized force, initially we compute the vector of generalized force generated by the group of thrusters. For the propellers, the forces and torques applied by the propellers were computed and mapped to the vector of generalized force. And for the servo motors, it was used the law of action and reaction, in which a torque applied by the servo motors generate a reaction in the main body of the Doutorado. So, and it is also considered a friction force. In order to compute the aerodynamic forces and moments actuating in the Doutorado was split into 5 aerodynamic surfaces. They are the fuselage, the wings right and left, and the tail surfaces right and left. For each aerodynamic surfaces, the drag, lift, and side force, and also the moments applied with respect to the frame positioned at the aerodynamic center of each aerodynamic surface were computed and mapped to the vector of generalized force. Since we computed the aerodynamic forces for each surface, it can also be considered the aerodynamic interference generated by one aerodynamic surface into other. To that, these forces and moments are computed through these equations, where the coefficients of the interference must be estimated via wind tunnel experiments or in flight. In the case of this work, the aerodynamic coefficients used to perform the numerical experiments were obtained via wind tunnel experiments conducted at the University of Seville. So, in a first controller proposed by this doctoral thesis to the Doutorado, we designed state feedback and output feedback linear double finch controllers for the Doutorado operating in the helicopter flight mode. To this, the environment wind is assumed as disturbances and simulated through the von Karman wind turbulence model. The output feedback controller is designed assuming that the Doutorado velocity x dot and y dot are not measured, and for the sake of comparison analysis, all the controllers were tuned with the same tuning matrices. Here is the results of the experiment. We can see that at the beginning, the Doutorado starts displaced from the desired trajectory and is designated to track this x-spiral trajectory, and at the end, it must stop and land at a final destination. Here is the quantitative analysis of the results, where we can see that although all the controllers achieved a good performance, the controller that was formulated considered the dynamics of the disturbances achieved a better performance with respect to the ISE and the ADU indexes. So we also proposed a nonlinear double finch controller for the Doutorado. In this case, in the case of the Doutorado, the rank of the input coping matrix varies in time according with the magnitude of the relative wind speed. Therefore, the controller that I presented for underactuated mechanical systems with input coupling is not suitable to be applied to this system. And therefore, in this doctoral thesis, we propose a third formulation of the double finch controller for underactuated mechanical systems, where now the mechanical system is partitioned with respect to stabilized, regulated, and controlled degrees of freedom. The objective is to provide trajectory tracking of the controlled degrees of freedom and set point regulation of the regulated degrees of freedom, while the remaining ones are stabilized. For the case of the Doutorado, it was selected as stabilized degrees of freedom, the roll and pitch dynamics, regulated degrees of freedom, the tilting angles of the servo motors and the yaw angle, and controlled degrees of freedom are the position of the Doutorado with respect to the inertial frame. So, for the sake of control design, the system was manipulated and represented in this standard form, P14, where we now take into account 3 cost variables, the cost variable ZC, the cost variable ZR, and the cost variable ZS. And the nonlinear double infinity control problem is posed taking into account the weighted subvolume norm of those three cost variables. This control problem was also formulated via dynamic programming, from which we obtain the expression of the optimal control law, the worst case of the disturbances, and we propose a particular solution to the resulting Hamilton-Jacob equation. And in this case, in order to map the generalized inputs to the control inputs, we propose a control allocation scheme. This control allocation scheme is basically a minimization problem subjected to time varying constraints. And the objective is to map appropriately the generalized inputs to the control inputs, taking into account the magnitude of the relative wind speed. So now I present a video of the experiment. This is the experiment. At the beginning, the Doutorado take off from a home point and is designed to accelerate in forward motion. During the experiment, the Doutorado is subjected to an environment wind with magnitude -3 meters per second applied with respect to the inertial x-axis. At the beginning, the Doutorado must accelerate in forward motion in order to transit from the helicopter flight mode to the cruise flight mode. During the experiments, external disturbances and wind gusts are applied to this system. When it reaches the airplane mode, it is designated to track a circular path. And at the end of this circular path, the Doutorado must transit again from the airplane mode to the helicopter flight mode, and at the end, land at the final destination and remain in this position. As can be seen here, the Doutorado accomplished the mission and reached the final destination. So, I will conclude the work. In this PhD thesis, the following contributions were achieved: the extension of the nonlinear double-two and double infinity control approach proposed in Aliu and Bocas to the weighted subvolume space, the extension of the successive Galerkin approximation algorithm proposed in BERT to approximate solutions of the Hamilton-Jacob equations resulting from the double-two and double infinity control approach, the proposal of the nonlinear double-two and double infinity control problems, and their formulation via dynamic programming for fully actuated, reduced, underactuated, and underactuated mechanical systems with input coupling, with analytical solutions for the resulting Hamilton-Jacob equation and the corresponding stability analysis. The establishment of the concepts of W stability and W gain for a general class of system, with the demonstration for the particular case of study, the formulation of the double infinity control strategy in the weighted subvolume space for linear systems via optimization problem with LMI constraints, considering state and output feedback approach, disturbances dynamics, and the stability constraints, a detailed modeling of the nonlinear multibody dynamics of the Doutorado using the Euler-Lagrange formalism, the design of state and output feedback linear double infinity controllers for the Doutorado to handle with the helicopter flight mode, taking into account the von Karman wind turbulence model, the extension of the nonlinear double infinity control approach of mechanical systems, with input coupling to the case in which the mechanical system is partitioned with respect to stabilized, regulated, and controlled degrees of freedom in order to achieve trajectory tracking throughout the full flight envelope of the Doutorado. As future work, we intend to implement the proposed control strategy in the real Doutorado. Besides that, we intend to use parallelization procedures in a GPU to execute the successive Galerkin approximation algorithm. Besides, we want to formulate the nonlinear double-two and double infinity controls for mechanical systems to avoid the use of pseudo-inverse mapping to compute the control signal, extend the nonlinear double-two and double infinity controls to the output feedback case, and design a robust adaptive mix controller to solve the full flight envelope tracking problem of the convertible T2 EV. During the development of this work, the following journal papers were elaborated and the following conference papers were published. Finally, I would like to thank the Brazilian support agencies, INSAC, CAPS, and CNPq, and also the graduate program in electrical engineering of UFMG, and a special thanks to my friends from Macro Group and Provant Group. That's it. Thank you.
Okay, thank you very much, Daniel. You reached the time. It was about 45 minutes. It's great. So I think now we can make that break I said before, and we can return in 35 minutes. It's about here in Brazil. It's 12 and a half. And okay for every members of the examination board.
Okay, para mim.
Okay.
Okay.
Okay. Perfect.
Ok, Guilherme.
Okay. Thank you. So, Luciano, nós vamos então fazer uma pausa agora e a gente retorna ao 12:30. Ok. Até logo. Obrigado. Okay. Perfect. Okay. So we are back here with the presentation. Now we start the second part of this defense, and as it's quite common, we start with the member far from here, and so I will start with Professor Manuel Ortega from the University of Seville. First of all, I would like to thank you to accept these invitations to the defense of Daniel. And so for me, it's a pleasure because it is my first PhD student that is defending, and to have you to be here with us, my advisor from my PhD thesis, evaluating my PhD student. It's a pleasure for me. So thank you very much, Manolo. Okay.
Perfect.
Okay. So go ahead, please.
Okay. Thank you very much, Guillermo. Then, first of all, I would like to thank Guillermo and Sergio for inviting me to be a member of the tribunal. And next, of course, I would like to congratulate Daniel, the candidate, for what I think excellent work. I would like to congratulate as well to the supervisor, to Guillermo and Sergio. And next, just to acknowledge the work performed by Daniel, the candidate, trying to summarize in just more or less 50 minutes a really nice presentation. So congratulations. Respect with the thesis, I would like to start just recommending to correct some really minor mistakes. For example, I think that this is a really good work. Sergio has told me that you have the opportunity to change something of the document, and perhaps it may work to correct some minor mistakes. For example, some of them, I think I'm going to pass you some correction, if you don't mind, to Guillermo or to Sergio, in order to correct the text, if you want, of course. Perhaps my first question, maybe something about, let's see, Daniel, what's the difference for you between a function and a variable?
My internet connection is not good. The voice is cutting. Can you repeat the
Yes, of course.
the question?
Well, I was reading the document. I have found some surprising definitions about X, for example, the state of the system, about the input, the control inputs. For example, let's see. I have written down here. Page 99. Sorry, 19.
19.
Just an example.
Can I share the document in my? Can I share my screen with the page?
Let me try, but I'm not sure to be able to.
I will share my screen with the page. Then you can see.
Okay.
Él la comparte, Manolo.
Okay.
This is page 19.
19.
Yeah.
Sorry.
Okay, 9.
10 also, yeah.
3.4.
Okay.
Yes, for example, here, just after that expression 3.4, you have written where x, depending of t of the time, is like a function which start from, I suppose that from the time, which is the real, the positive real set to, of course, to the, I can't read that, but I suppose that to the r to the n. When someone defines some expression like that, at least for me, that definition is like a function, not like a variable. If I well understood, at least
The definition of x.
Yes.
X. Yes, I define x as a function of the time.
Okay, but let me to repeat the question. For you, what's the difference between a function and a variable? For example, for me, it's quite usual to read belong to r to the n.
Yes, I decided to define the state vector like this because if I say that x belongs to the real space with dimension any x, this means that x is an element of the space and not a function in the space. So if I define that x belongs to this to the r and x, the x would be a constant.
Okay, perhaps this is just some difference of understanding the definition. So anyway, no problem. It's a minor remark. Another question, please. Let's say, for example, expression 4.9 and 4.23.
4.9.
Okay, just for example, you have there a function b2 which depends on x and explicitly on the time, on t. And just more or less the same with the w infinite is the expression b infinite of the page 35. So the question is, you have proposed some Galerkin algorithm to try to approximate a solution of B2 and B infinite. How do the proposed algorithm take into account the explicit dependency of the time?
In this case, we are formulating the control problem assuming an autonomous system. So for this system here, we don't have an explicit dependency on time. For this,
it may work to. Yes, but
and because of this, this function here does not explicitly depend on time.
But the function B2.
Yes, but yes, we are approximating a solution in which this partial derivative here is equal to 0.
Okay, perhaps it may work to explain that point in the next section. If you will remember the 4.2.
Okay, I will improve this explanation.
Okay, another question. I have read in the document that you have performed some experiment and you have synchronized some controller, including the decision of select some specific weights for different controllers, for W H and W H infinity, W infinity and W2 controllers. My question is, have you tried to propose some rules to synchronize the controller, the weights at least of the controller? In other words, how do you have selected the specific values of those weights?
In this case, I tuned the controllers based on trial and error, based on my experience with the system.
And do you think that it's maybe possible to try to give some insights about how to select them?
Yes, I think I can include in the thesis a way to how to start tuning. Actually, I started the tuning by using an approach. I don't remember now the name of this, but I started by weighting the variables as 1 divided by the max deviation that I want from the desired value, and then I performed a fine tuning over this initial tuning. And I remember this initial tuning has a guy that proposed this approach, and
Bryson.
Yes.
Bryson.
Yeah. I started tuning using the Bryson method, and over the tuning with the Bryson method, I performed a fine tuning. Okay. So I can include this explanation in the thesis.
Okay. Another recommendation, of course, if you want to take into account it, I'm using the test some explicit expression of the applied torques, for example, to the controller designed for the quad rotors, starting from page 90. Sorry, I think it was 90. It was 17.
17.
So, yes, you start to design some controller. One of them is just an example.
In what page?
Okay, you start there. Let me find it. Okay. I'm sorry, it's a bit difficult to speak and to manage the file at the same time. Okay. Okay. Remember, this is just an example. You start to design, for example, a controller for the quadrotor UAV at page 70, and then you finish showing some experiments, rates, but I miss, in some sense, the explicit expression of the torques applied to the the control signal, applied to the quadrotor in order to achieve that results. So perhaps may be great if someone may read those explicit expression in order to copy, for example, the expression into a computer and be able to try to reproduce the experiment. I don't know if you understand me.
I didn't understand that very well, but because of my internet connection is
No, sorry for my English.
your voice.
Okay, anyway, it doesn't matter. Just a couple of questions, if more if you don't mind. When I was reading the thesis, for me it was a bit strange, the structure of the thesis. I mean, I think I know that it may be difficult to try to include in the thesis everything you have developed during those years, and of course, I know Guillermo, I know Sergio, I know the project in what this is involving. But anyway, you have developed a really theoretical thesis, starting from the first chapter to the sixth one, including some numerical examples at the end of each section of the chapter. And then in chapter 7, there's I don't know why, a new case study, which is a bit strange to include that case study there, taking into account that you have already included some numerical sample, including, for example, some, let's say, experiment with a quadrotor helicopter. So the question is, I guess the answer, but I have to ask the question. The question is, why have you included that case study in that chapter 7, in the thesis?
The idea when we proposed the project of this PhD thesis was to develop controllers for the TutuHotAV, and we were supposed to start by trying to apply the H-Finch controller and also trying to formulate these controllers in the weighted topological space. But when we began formulating these control problems, we saw that the formulation of the controllers in the weighted topological space was a contribution, and this contribution was evolved to a main contribution of this thesis. But the problem of designing a controller for the TutuHotAV is also a big problem in the literature. As I said in the presentation, the design of a nonlinear controller to solve the full flight envelope trajectory tracking of the TutuHotAV is an open problem that's quite hard to solve. Because of this, I decided to first present the formulation of the controllers, and at the end of the manuscript, present the case of study of the TutuHotAV. That's also a main. It's the main contributions of this work, and because of that, we decided to split this presentation, this thesis, like this. We start by formulating the controller, and then we employ this controller in the TutuHotAV. But all these topics are main contributions of this work. And
okay. That's right. That's right. Perfect. Let me ask you the last question. I've seen that you have dealt with the rotor problem of the transition between modes. Perhaps I haven't understood really well, but for example, the figure 7.13 figure in page 131.
The figure.
Right. Yes, this one. I have understood in the presentation that that figure represents more or less the way in which the let's say the aerodynamic forces change with depending of alpha. Maybe. Is it right? Or,
The aerodynamic forces are computed taking into account the alpha, that's the angle of attack, beta, that's the side slip angle, and also the magnitude of the relative wind speed.
Okay. In any case, could you repeat? Sorry, Daniel.
The aerodynamic forces and moments are computed taking into account alpha, that's the angle of attack, beta, that's the side slip angle, and also the magnitude of the relative wind speed that depends on the aircraft velocity and also the environment wind speed.
Okay, perfect. My question is that those relationships are static, I suppose?
No. When the aircraft start moving, it changes the aerodynamic, the magnitude of their relative wind speed, and also the environment wind change this magnitude. So it's time varying variables. They are time varying variables.
Yeah, okay, it doesn't matter. Perhaps we may discuss this question in another occasion. Don't worry. That's all, Daniel. For my part, congratulations again. I think that you have performed a really good and excellent work indeed. By the way, Guilherme, I think that I'm the unique not Brasileiro spoken person here. So feel free if you want, of course, to speak Brasileiro. I think that I'm able to understand you more or less, and perhaps for you is a bit more comfortable.
Yeah. As
feel free. Feel free if you want. For me, perfect. If you don't want, for me, perfect as well.
So Manuel, can you repeat the first part because I didn't understand this?
Feel free to speak Brasileiro if you want.
I didn't understand the
Guilherme, he told you that.
Okay. Portuguese. Okay. No, I don't know. It depends on the other members and Daniel. But if for you it's okay.
Yeah, for me it's okay.
Okay.
I think we can try to keep speaking English, and if I have some problems with answering the questions in English, we can change to Portuguese just to answer some specific question.
Okay, as you want, it's okay. For me, it's okay both in English or Portuguese, and so it is with you, Daniel.
By the way, I didn't want to say Portuguese because you're from Brazil.
Okay. No, for me it's okay. But I leave Daniel free to choose if in Portuguese or in English. Maybe, as he said, he can keep in English. And so, but okay. So, well, thank you very much, Manuel, for the nice comments. I have made some notes here, and so after we can talk about. So now I pass to the second member of the examination board. I'd like to thank you again to Professor Adriano for accepting this invitation. So thank you, and Daniel is with you.
Okay. Thank you, Larry. I speak in English, but if I have some problem, I will also try to speak in Portuguese. So, First, I would like to thank you, Daniel, and Professors Guilherme and Sergio Esteban for the invitation to participate in this board. I would like also to congratulate you, Daniel, for the thesis. It's really outstanding work. With you have a very strong theoretical approach with the Sobolev norms, and also the case study in the end is the final good work you have done is perfect. It's very nice, and also it is a novel, okay, about the VTOLs. During when I was reading your work, I received a notice about VTOLs and send you by the chat. If you can show in the representation your screen, the chat. I sent by the chat.
The chat of the. Let me try here. Okay, do you want me to open the links, right?
Yes. It's a VTOL that was developed in UK, I think. I remember.
Yeah.
Can you show in the screen?
I'm showing the wrong screen.
To the others colleagues.
You need to share a screen, not PDF.
Whoa.
Oh.
Share. Screen. I think I can show PDF. Are you seeing it now?
Yes.
Yes.
So I have received this news about this aircraft, and I was reading your book, so I remember to show you this aircraft, and actually it has a different configuration of rotors, but also is a VTOL. I think you can see others pictures of this system in the. But I don't know if it is already built. Okay, it says it's in development now. But it's I will have a video, but only to show you that the topic of your case study is very new and important nowadays, no? To the literature. Okay? So it's only this point. About the book, I have only 2 points that I would like to mention. Is on page 39, figure 4.1.
Let me share again.
It's the model of the. Okay.
And page. What's the number of the page?
39.
39.
39.
Okay. 39.
This model, I think you can improve the definition of the angles. It's not usual to define the angles in this form. I think it's better word even to put the vertical bar in a different position or something like that. But it's only it's up to you to change or not.
Okay, those angles are defined in this way because I picked this model from this work here, Madeo and Hoff.
Okay. Okay, it's up to you too. Another figure is, let's see here, figure 7.12, 128, 128. This graph is not so good. I can't see the difference between them. So if you can show a zoom about the variables, it would be better.
Okay.
So
Yeah.
about the questions, I have one, a few questions, only a few questions. The first one is, how many terms do you need to define in the Sobolev norms? For example, page 48, equation 5.9. We have defined 4 terms to the Sobolev norm. Okay? Why you have defined 4 here, and why you have defined 2 and 3 in the others controllers?
Okay.
What is the reason to define the number of terms in the norm?
The idea here is to include the dynamics of the system in the class functional. In this case here, for example, we have the integral of the error of the controller degrees of freedom. And the mechanical system is represented by the error of its second time derivative of the degrees of freedom. Therefore, when I take the time derivative here, so in this case, the norm of we have the norm of the variable z, its time derivative that takes into account the error of the controller degrees of freedom. Its time is twice time derivative that takes into account the first time derivative of the controller degrees of freedom, and also the 3 time derivative of the stabilized of this cost variable z that takes into account the double time double time derivative of the controller degrees of freedom. So with this we include the dynamics of the system here. As if you look here, the control degrees of freedom is represented by isolating this.
Okay.
It's the dynamics of the control degrees of freedom.
Okay, I haven't understood. But
Yeah.
if you have defined the z variable in 5.8 as position error, you will need to define only 3 terms. It's correct?
Yes, you're correct. So, but if I define as the arrow here, we would not consider the integral action into the design of the control.
Okay, but you need to define 3 terms in the functional.
Yeah.
Okay. So I think you have to write this remark in some point of the, because some functionals have 3, 2, or 4 terms in the Sobolev norm. So it's better to.
Yes, I agree with you. I have not explained it very well, how to choose the number of time derivatives that we are including.
Okay. Now page 55. It's 55. And in the remark 27, you say that W2 and W infinite are equivalent for this system. And after equation 5.57, you say that the worst case of disturbance is 0. I think it's strange to say that the worst case is 0. How can you explain me this?
Yes. What's the number of the question again?
Página 55. Página 55.
Here, where the worst case of the distance is equal to 0, where?
É na equação 5.57, logo depois da 5.57, você fala que o pior caso do distúrbio é 0. O pior caso é quando é 0, e quando não é o pior caso é diferente de 0. Fica meio estranho isso, né?
It's strange, but it arises from the formulation of this controller. And the idea here is that we was researching. We were looking for the answer for this to be equal to 0, and we was thinking. I think. Can I answer this question in Portuguese?
Yes.
A gente andou pesquisando o porquê que esse pior caso da perturbação é igual a 0, e aí a gente chegou na seguinte conclusão. O que acontece? Nesse problema, deixa eu só voltar na expressão do pior caso da perturbação. Assim como nesse problema, assim como no problema formulado considerando o sistema mecânico completo, nós temos que o espaço-imagem da perturbação e o espaço-imagem das entradas de controle são iguais. Por causa disso que a gente não tem um pior caso da perturbação. Porque qualquer perturbação que seja aplicada no sistema existe. Não quer dizer que a gente consiga ter, mas existe uma lei de controle que consiga compensar essa perturbação. E a gente também consegue demonstrar que se a gente multiplicar essa matriz ou essa matriz por alguma combinação linear ou não linear dessas colunas, a gente também chega na conclusão que esses controladores são equivalentes. Então, se existe um pior caso da perturbação, ele tem que estar num espaço nulo onde eu não consigo compensar ele utilizando as entradas de controle. É alguma perturbação que atinge algum espaço imagem dessa matriz de perturbações em que eu não consiga compensar usando a entrada de controle. Isso é o pior caso da perturbação. Nesses casos aqui, como a gente tem o mesmo espaço-imagem para perturbação e para entrada de controle, a gente não tem um pior caso da perturbação. Isso é o que a gente chegou na conclusão, avaliando esse problema.
Ok. Fica um pouco estranho, né? Mas...
É um pouco estranho, mas...
So, the Sobolev norm is a general case of the H-infinite norm. It could be, I can think about this or not?
I don't think so.
Okay.
I think the Sobolev norm is... No, I think we cannot say that. Okay. It's a constrained case, but we cannot say it.
My question is, for this for this kind of system, the same system, when I use a height infinite controller or a height 2 controller, I have two different controllers. Yes, or here you are saying that the both controllers are the same.
Are equivalent, yeah.
Are equivalent. But if I use the traditional height 2 and height infinite norms, they are different.
Yeah.
For this special case of this system, do you know something about this?
The H2 and H-fin controllers are different for this system.
Okay. I don't know.
I think this case in which the controllers become equivalent only arises in the formulation in the weighted wire space.
Okay. Okay. Good. So the next question is page 23, página 23. After the remark 10, you say that the minimization of gamma results in controllers that provide faster disturbance attenuation. Okay. And this is the main feature of the height infinite control in sub-level space. Okay, but why you have affirmed this?
The idea here is that in this case, gamma is an upper bound for the energy induced by the disturbances on the output variable, that's in this case we consider as the states of the system, and its time derivative. So when we minimize gamma here, we are minimizing the energy induced by the disturbances on the cost variable and also in its time derivative. So since we are reducing this energy in its time derivative, we are obtaining controllers that provide a faster disturbance attenuation.
Okay. Yes, I haven't understood this exactly as you have said, but it's better you to write this in some point of the test or something like that. And this is related with my next question, which is exactly the same as Professor Manuel has asked you about how did you tune the weights, and what are your feelings about how you tune the weights? Because when I have a proportional gain in a second order system, I know that if I increase the gain, I have bigger overshoots and so on. Okay, the system is faster and something like that. It's basically the same as a proportional derivative controller, or it's different. The weights that you use in the position and the time derivative of position, something like that.
Actually, I didn't explain it, how did I tune the controllers here, but in this case, I tuned it, as I explained to Manuel, I tuned the controller using the Bryson methods, and then I performed a fine tuning, a fine tuning over this initial tuning. And I answer your question.
É.
So, okay.
Mas vou concluir em português aqui para facilitar um pouco. Quando você está ajustando lá o peso do elemento derivativo, por exemplo, né? Lá na norma você tem 3 ou 4 termos lá, um deles é o derivativo, o outro é a aceleração. Quando você ajusta um desses termos, como que o sistema se comporta, né? Você conseguiu sentir isso, assim, de você aumentar muito o ganho, o peso do derivativo, ele vai ser mais amortecido. Vai responder mais rápido, com mais amortecido, ou sei lá, alguma coisa do tipo.
Actually, in the weighted Sokolov approach, the tuning is a little bit different of the tuning of the H-finch controller, since now we are not weighting the control input, we are weighting the function z and its time derivative. And as you said, when I tune the integral action and the arrow, we have the same behavior as tuning the integral action and the arrow and the time derivative as in the H-finch controller. But when it comes to the tuning of the dynamics of the system, we have a different behavior. In my experience here, if I tune the dynamics of the system, if I put more weight in the dynamics of the system tends to converge slowly to the desired trajectory and tend to not go out of this desired trajectory when the disturbances are applied in the system. That's the difference. While in the H-finch controller, you tune the control input and you don't know what will happen with the system. We know, you know, actually, but when you tune a control input and the system is coupled, this control input modifies the behavior of the entire behavior of the system. Here we tune directly the variable. For example, in the case of the Doutorado AV, if I'm seeing that the servo motors are faster and have a fast dynamics, and I want to slow it, I can increase the tuning or decrease the tuning just for this variable. The angle of the servo motors, the integral action in the angle of the servo motors is a bit different of the tuning in the H-finch control.
Okay. In the H-infinite control, usually we use some weighting functions in the frequency to tune also the. Can you use the same thing here with the Sokolov?
I didn't understand very well your voice. Can you repeat?
Em controle H infinito, a gente geralmente usa algumas funções de ponderação, são definidas na frequência. E a gente analisa a função sensibilidade complementar na frequência, né? E aí cria aquela planta aumentada. E a gente usa essas funções de ponderação para ajustar o H infinito também, né? Você já viu isso? Não está lembrando.
Eu já vi, mas nunca trabalhei com isso, assim, de forma... Mas eu já vi.
Sensibilidade mista, né, que eles falam, acho que é isso. Uma coisa do tipo. E você tem lá as funções peso que você pondera e ajusta o controlador. Eu queria saber se daria para usar de alguma forma aí com as normas também. Eu acho que dá. É só outra forma de ajuste, né? Eu nunca tentei isso.
Provavelmente dá para fazer, mas aqui, como a formulação já nasce no domínio do tempo, eu não tentei. Não sei, assim, te falar agora se é possível ou não possível, mas acredito que dê, sim.
Okay. So I think it's only these questions and this comments about your thesis. It's really a very good work. Congratulations.
Thank you.
Thank you again for the invitation. Thank you, Guilherme. Obrigado.
Thank you, Adriano, for your consideration. And also to
Guilherme?
I'm just listening from the YouTube because my mobile internet is.
O seu som não está muito bom.
So I'm in the iPad, so sorry for the time delay. Okay, thank you very much, Professor Adriano. Nice questions. This last one is a very interesting point. I will comment after. So I work a little bit with my advisor, Manuel Ortega, that's here. He worked a lot with this kind of mixed sensitivity and 8 infinite for linear systems. And so it's quite nice. And so thank you for the comments and questions. It was very nice. I make some notes here, and so I try to comment after, and that's it. So thank you. All right. So now we are now in the PPG in the graduate program of electrical engineering, and now. So I will start with the professor that is the distance is longer from the FMG. So I'd like to thank you, Professor Leonardo Torres, for accepting this invitation also. So thank you very much, and it's a pleasure to hear you now. And so Daniel is you. Thank you.
Well, thank you very much, Daniel, Guilherme, and Sergio. I hope I have pronounced Sergio correctly. So it was a pleasure to read your work, because it is it is a confluence of many different approaches to control that are being put together by someone that is trying to master the subject, so we can really follow the reasoning that you have employed during the development of the theoretical background in the thesis, and this was very fine. And surely, since you have so many publications, I feel very comfortable in being here in this examination board, because your work was actually already tested in relation to novelty, right, and correctness. Well, but I think that you need to improve your text to better reflect the quality of your work. Your thesis, I think that I think that I've mentioned this during your qualifying examination, that I could see the quality of the work, but well, in my opinion, your text has improved a lot since the qualifying examination, but I still think that you can improve it a little bit more in terms of rigor, mathematical rigor, okay? So I've made a lot of annotations to the PDF in order to help you with that, right? So I hope you have understood what I'm saying. Let me rephrase it. The work is a very nice work, and surely you deserve the title of Doutor em Engenharia, right? I'm not questioning this, but maybe you have missed some opportunities to have a text that can be referenced in the future by other students, you know? For example, the explanation of, or the overview of the successive Galerkin approximation algorithm is really superficial, right? And you are using some symbols and some nomenclature that you haven't really defined in the thesis. And if you think about it, this is very important in your work, right? It's a core part, and it would be very nice to have this well explained to your readers. If you want to have your work as a, let's say, primary source from which other students will get ideas and understand how optimal control is related to robust control and so on and so forth, right? So, but I've made these annotations, and you will find it when I send you the PDF that I have annotated, okay? So it's a general remark, hoping that you will be able to improve your text, because, you know, it's a really nice work, right? So I wish you can do that, okay? Well, and I can see that you have worked very hard, because there are a lot of things going on in your thesis, right? Especially, and from the question by Professor Manuel about the incorporation of chapter 7 in your text. Yeah, it seems it's really odd, that chapter 7, because there is so much work there that seems detached from the main work, right? And you can feel that by reading your thesis. And actually, to me, I don't know if I'm right, but to me it seems that you have worked very hard with the tilted rotor UAV, and it was a large part of your work, and you had to register in your thesis. Maybe this was the main driving motivation to have chapter 7. Am I right?
Yeah.
Okay. And so I'm okay with having chapter 7 there. But in the structure of your thesis, since you have very important, let me say that, very important details, because if you don't have those details that you have registered in chapter 7, anyone wouldn't be able to reproduce your results, right? So they are very important, and there are some very relevant questions to aerodynamics that's probably a contribution to to the area of aerodynamic design, right? So you have so I'm not saying that the material is not important. It is, but it breaks the flow of the thesis, because the majority of the thesis is about control theory in a more general setting. So maybe some of the details could be in an appendix, not because they are not important, but just to improve readability, you know? They are actually very important, and they are contributions in themselves. I can see that, right? And still, with regard to the thesis structure, I think that it would be very nice to try to combine chapters 2 and 3 in just one chapter. Because in chapter 2, you are doing a literature review, right?
Yeah.
And you start already using many symbols, concepts, and definitions that you need to separate or to better emphasize the contributions of your work. But you haven't still defined it yet. Many of these concepts and definitions, you don't have the definitions yet. So I don't know. Well, my suggestions would be to the first one would be just to mix both chapters in just one chapter, in which you start presenting the definitions, the concepts, and then you, at every opportunity where you find appropriate, you bring up one of the references, right? To say, in this work, this part will be different from this and that work, but you will have just explained the concept before, you know? For example, the weighted Sobolev norm. Or this is a little bit difficult to do. And maybe the second option is easier to implement, which is just to exchange the order of the chapters, to present chapter 3 first and then chapter 2. Maybe this would improve the readability in the same way that I'm talking about. Okay. Okay. Another general observation that I would like to do is that, and actually let me pose this as a question to you. The equivalence between the W2 and the W infinity control problems that you mentioned in remark 27, that is on page here. Remark 27. It's chapter 5, I guess, right?
5.
Yeah. Oh yeah, page 55 of the thesis. You have remark 27, the equivalence between the W2 and W infinity controller, right? This is something that you have to say more about. Do you agree? Because this is weird, right?
Yeah.
But let me pose this as a question for you. What do you think about a optimal control problem where you have a quadratic functional coast and a nonlinear system, but affine in the control and disturbance inputs. And you have an infinite horizon, right? So we have a quadratic coast, infinite horizon, input affine, nonlinear dynamical system. So if you have these properties and your performance output that you have been calling Z, the Z variable, right? If the Z variable is equal to the state, I think, and I would like to ask you that, I think that you will have this equivalence too, right?
In section 4, in chapter 4, we formulated the double two and double infinity control problems here, and we didn't got this equivalence. Those are the expressions for the worst case of the disturbance and the optimal control inputs. And here we don't have this equivalent.
Yeah, but if you pay attention to expression 420, it's very similar to feedback linearization, right? Because you are going, when you substitute back on, if you consider, when you substitute back on the system, it seems that you are feedback linearizing the system, and the resulting closed loop system is a linear time invariant one, right? And since you have an infinite horizon post functional, you know that you can solve the problem by using a quadratic Lyapunov function, right? You can use the LQR infinite horizon results to show this, right? So I think that the equivalence between the W2 and W infinity control, and you should think about it, it's actually related to the structure of the problem, the way you have structured it, in the sense that you have these elements: infinite horizon, functional coast, quadratic functional coast in an infinite horizon setting, and nonlinear dynamical systems, but with affine input and disturbances in the system equations, in the system dynamics. So think about it. I think that if you go through these steps, because I've tried to do that, and maybe I've made some mistakes, but you are the expert, right? So if you go through these steps on the, for example, W infinity control development and the W2 control development, I think that you will end up with an equivalent controller. So the problems are not equivalent in the sense of defining them, but you are actually having the same controllers, right? You are designing the same controllers, but it's not that the problems are equivalent, but you are having the same controllers. So if you think about the H2 and H infinity control approaches, you answered Professor Adriano by saying that in the H2 and H infinity control approaches, you will have different controllers, right? But if you have this structure where the performance output is just C, a matrix C times X, right? For example, it's likely that you will have the same equivalence. So think about it, right? Even in the H2 and H infinity control approaches. And this is a discussion that would be very nice to see in your thesis, right? Because another question that someone could elaborate after reading your work is about the connection between the same question that was asked by Professor Adriano, a question about the relationship between what we have already been what we have been using regarding robust control and what you are proposing in your work. You see, the H2 and an H infinity control approaches, they are very general, right? And I think it's not hard to see that you could define a performance output in an H infinity setting where you decide as one of your performance outputs the time derivative of the states. You see? Good. Wait. Yeah?
Yeah. The difference here is that I think using an H infinity performance, we cannot include the dynamics of the system in the cost function.
I mean, you can, because in the general setting, you are free to choose. Think about the linear time invariant case, right? You are free to define the C and D matrices. Do you agree? For H infinity? Because,
yes.
I mean, you are free to define the performance output that you are going to look at to minimize the induced L2 gain, right? So you are free to actually say that part of your performance output is just A times X plus the matrix that multiplies the perturbation times the perturbation if you want, plus BU, right? You can do that. And you would be waiting, also waiting the time derivative of the states. What's really nice about your work, Daniel, is that you went back to the origins, you know, of these whole ideas and concepts, and you managed to show that, that's my point of view, of course, and managed to show that there is a nice way of deriving the results without having to go into the generality of the problem of H2 and H infinity control problems in the way they are now defined in the literature, in the textbooks. Okay, but I think that they are very closely related, and it would be very nice to explore this a little bit better. And by doing that, your work, I think, will become a much more valuable source for new ideas for other students, right? And by saying that, I think that it becomes clearer that some contributions are really related to under-actuation, right? The interplay between under-actuation and optimal control. And so specifically for Euler-Lagrange systems. And so this is another aspect of your work. I think that you have many things to say regarding this aspect of your work, right? And you have registered in your thesis. But well, some things I think need still more clarification. For example, regarding the sigmoidal function that you have used to try to smoothly go from the helicopter mode to the aircraft mode, right? So it's interesting. It's an interesting idea, but I've got the impression that you didn't manage to prove that the whole strategy would stabilize the system. Am I wrong? I mean, what I'm saying is that you have incorporated that optimizations, right, to find a pseudo-inverse like relation, but this has broken up the flow that you have been following, the approach, the sequence of steps, right, that you have been following to prove stability and performance achievements for the closed loop controlled system. Am I right?
Yes, you are right.
So maybe you should emphasize a little bit more. You have done very nice things. So what I'm saying is maybe to highlight this a little bit more will give others the opportunity to contribute in the same vein that you have been contributing, right? For example, one important question is about the differentiability of your control action if you are relying on that pseudo-inverse step through an optimization process, right? I think that, and I would like to ask you, I think that you are losing guarantees that you will have a smooth control action. What do you think?
Because of the control allocation using the minimization problem?
Yeah.
I think I have a continuous solution, a continuous control sign to apply to the system, because the sigmoid function is smooth, and since we are dealing with a continuous system, we cannot jump from one control input to other.
So maybe this would be worth showing, right? Or at least commenting about, right?
Okay.
Okay. What else? I'm just going through your text now. I'm just looking if I want to say something beyond what I have already said. Okay. Well, I have other observations, but I just left them in your PDF text. You will see. And well, let me just say the last thing that I would like to say about the chapter on W infinity and W2 control for linear time invariant systems. I think that it's chapter 6. Yeah, chapter 6. I think that especially in this chapter, it's very difficult. It's a very difficult chapter, and I think that because you have so much material already developed, right, about robust control of linear time invariant systems, and it's very odd to not have comparisons with the state of the art, you know. And so I see that you have tried to understand what would be the results in this much more strict case, which is the case of linear time invariant systems, right? I do appreciate that, but I don't think it's fair. I don't know how to say that, but you do have so much material, right, on robust control of linear time invariant systems that, for example, when you say something about robust control with respect to parametric uncertainties, you have decided to use a quadratic Lyapunov function with a constant matrix P, right? In a polytopic description for the parametric uncertainties. So this is correct, this is okay, but this is nowadays considered as a very conservative option to deal with the problem, you know? So I think that chapter 6 could be an appendix too, could be moved out of the main flow of the text. But it's just a suggestion for you, okay? I wonder what professors Ricardo and Victor will say about that. But you know what I'm trying to say, right? I think that you have a strong coupling that you haven't really explored between H2 and H infinity and W2 and W infinity. And this would be the thing that I wish I could see on chapter 6, right? The exploration of the connections between these two words, because they are surely very connected, right? They are very, yeah. I think you understood, right?
Yeah.
What I'm trying to say. So that's it. Congratulations for your work. I think that you have a very nice material, and you definitely have novelty in your work as reflected on the published contributions, right? And I just want you to consider my annotations if you are magnanimous to do that. And maybe I can help in the process of getting a nice future source for future students. Okay?
Mm-hmm.
And thank you.
Thank you all. I will try to consider all your considerations in the thesis and improve the document.
Okay. Thank you.
Thank you.
Okay, thank you very much, Professor Leonardo. Again, your comments were very good, and you went to the point. I can say in some questions. I think it was very specific, and that's very nice. Thank you a lot for your consideration. So now I invite to talk to make questions Professor Ricardo Takahashi. Thank you again for accepting this invitation. Thank you.
Thanks, Guilherme, Daniel, Sérgio. I start my comments saying that your thesis, Daniel, is really very good. I think that you achieved some very nice results that may become really relevant. And my comments perhaps would try to indicate some aspects that possibly could help to indicate how to present those results in relation to former results that are already existing in literature. My comments in a large extent will be similar to the ones by Leonardo and some comments by Adriano, perhaps with a small difference of perspective. Let me follow the sequence in which the issues appear in the text. Please go to page 19. In equation 3.6, you present you say that the H2 optimization would like to that minimization of the trace of the output, the quadratic output. This is a bit strange, because you say in the expression that tau, the control input, must be in the L2 space, but you don't specify what should be the noise or the disturbance input W. And of course, if W is persistent, for instance, this integral would be infinite. I think that there is something wrong here. What you say?
Yeah, indeed, there are some gaps in this section, and I have to improve it.
Yes,
one of the gaps is this gap that you said. We are not defining. We are not saying anything about the disturbance here.
I think that you perhaps have tried to write an expression concerning the h, the small h, as if were the output from a Dirac delta input. In that case, the expression would be similar to that. Perhaps there is some confusion here.
Yes, I have to define better its terms.
Let's go to page 20, the next page. Say just after remark 1 that the control problem 3.7 is general and can be employed to synthesize an H2 controller for the nonlinear system. My comment here is that the 3.7 equation, it's just the former page. It in the case it was stated in the case of the 3.7 in terms of the inputs composed by delta Dirac functions, so that you have the classical statement for the H2 cost function. However, in the case of nonlinear systems, that statement based on the Dirac delta function, I'm afraid that the meaning is not preserved in the case of the nonlinear system. I think that the statement of the problem would not be based on the formulation starting from the Dirac delta function. What you say about this point?
The idea in this point of the manuscript was to introduce the double two control problem in the frequency domain as it was originally formulated, and then show how the formulation in the time domain was obtained from this original formulation. And in this work, I think is this one here, yes, this one, they demonstrate that if we consider the disturbances equal to a delta Dirac and minimize the energy of this cost variable here, this is equivalent to the H2 control problem in the time.
In the linear case, I'm asking if in the nonlinear case this is still the case.
And you can say no.
No, it is not, right?
Okay, perhaps reformulating this section would correct this issue. Let's go to page 43, 43.
Just let me. Did you note this in the manuscript that you are going to send to me?
Yes, yes. It's
okay.
I'm following some notes in the manuscript.
Okay.
In page 43, in fact, I've annotated some questions that are general questions about this chapter. First question, in your simulations of this chapter, you present the algorithm for W infinity controller, and in that case, there is a step in the algorithm in which you must find the worst case of the disturbance W. It's just a curiosity. What's the appearance of that signal? Is it, in the case of H infinity, in the linear case, H infinity controls, the worst case disturbance is a sine signal, a sinusoidal signal. What's the appearance in the case you are studying?
In this case, the worst case of the disturbance is a function of the states. The worst case of the disturbance is a function of the states and some variables related to this.
I would like to suggest to put a figure. I think that for someone that is familiar with the linear case, when someone with this background find your thesis, I think that this is a curiosity that will appear.
Yeah, but I don't know how can I plot this. I think this expression is a particle for in each system.
Yes. I'm saying that you can plot in the example.
Okay, like a 3D.
Yes.
Okay, I'll try to do this.
Just a question about this. Don't you find a final expression of the disturbance that is the signal that you find after finding the optimal controller?
Your voice cut for me. Can you repeat?
Em português. Será que você não encontra um sinal que seja completamente assim, que seja o formato final do sinal de perturbação de pior caso quando você chega ao final das iterações?
I have to plot this signal to see.
Okay. You have not tried yet. Okay. Another curiosity. I think that the W2 design, in the W2 design, you also supposed a Dirac delta as the input in order to calculate the optimal W2 controller, correct?
I have not used the delta Dirac.
Let me find the equation. I'm not finding here. I will send you the text after the defense. You find that. Next question. Oh yes, I think that it's important to show the expressions of the controllers that you find in the examples. Of course, there are large expressions that perhaps will take you one full page to show, but I think that it's important to show those expressions, mainly because, for instance, in the case of the UAV system and the other similar autonomous systems, those controllers must be implemented on board. So it's important. A relevant issue is to present what are the computations that will be performed in real time by the system.
Okay. In the case of the controllers presented in chapter 4, I will include here the expressions of the control tools. And in the case of the controllers proposed for mechanical systems and the controller proposed for a T2 AV, the control laws are computed taking into account the matrices of the system. So do you think that I need to write, to give the explicit?
I think that if possible, you could include, of course, it may be very difficult, but if you include it perhaps in an appendix, it would be welcome.
Okay, I'll try to do that.
Let's go to page 48. 28. Remark 23. You say that the remark 23 says that, in contrast to the nonlinear H2 and the H-infinite control approaches for mechanical systems, the proposed W2 and W-infinite controls do not include the control inputs directly in the cost functional, which relaxes the requirement that tau of t belongs to L2. In addition, this relaxation allows formulating the control problem without any prior compensation of the gravity vector. I ask you, I think that you need that the relative degree of the system should not be 0, because if this were the case, this would lead to the same problem with the H-infinity H2 controllers.
I didn't understand very well the question.
If the relative degree were 0, were not at least 1, the control input would be appearing in the output. So this comment would, I think, would not work.
The relative degree?
Yes, think about the relative degree. 0 means that the output has a component that is the input.
Yes, but in this case, the output, there's no component that's the input. In this case, the input appears here in the fourth time derivative of this variable z with respect to the disturbance, but this is an equation. Let me see the expression here. This is this term here with this inverted and this in the right side of this inequality. And when we take the L2 norm of this equation, it's different of taking the L2 norm of each component and sum. So we can, for example, use this term to sum this term, and we have to take the L2 norm of the whole expression. That's why we don't require that this control law here belongs to the L2 space.
Okay, I'll think about that. I'm not fully convinced, but I will think about that.
Okay, I think I have a better explanation here. Let me go background. In this case here, we note, we highlight that the L2 norm of x dot is the L2 norm of this expression here that's different from the L2 norm of each component separately. That's why in this case, we are computing the L2 norm of this whole expression. That's why we don't require that this control input belongs to the L2 space. We require that x dot belongs to the L2 space.
Okay. Let's go to page 88. When in page 88 you proposes a formulation that considers the dynamics of the disturbance, I think that here I have a comment that is similar to a general comment by Leonardo. I think that such a formulation is quite similar to several things that we perform in the usual formulation of H2 and H infinite controllers, putting the dynamics of the channel between between a white noise theoretical signal and the signal that effectively disturbs the system is a quite usual approach, and I think that it's important to I think that in this case there is not really a difference from the usual approaches that have been used in several places. In fact, you are augmenting your system with another system that performs this modeling of the input channel. I think that of course it's important to present this issue in your proposal. It's relevant to show that it is possible to do, but it's not different from other kinds of approaches. And I think that in the case of the response, it's not specific in this page. It's more diffusely said on the text, but this is the moment to say. I think that the issue that your controllers based on W2 or W infinity approaches, they track the reference input faster than H2 and the H infinite controllers. I think that this also should not be stated in this way, because the treatment of a tracking problem, we should expect that would be performed with a bit more complication than the basic formulation of H2 and H infinity. Leonardo said that a possible way to consider the same thing you considered in your approach was to put the derivatives of the states in the output signal, so that the H2 H infinite controller could deal with those signals in the same way the W2 and the W infinity controllers do. I add to that observation that, for instance, it's not only the H2 and the H infinite controllers that do that, but several other controllers can do that. The dealing with the tracking problem in most of the cases would require, for instance, the usage of feed-forward control action that would compensate the reference signal that is known a priori. You know a priori what will be the disturbance. We should not. It's not smart to wait until the reference signal to change the system variables in order to compensate for that. I think that the analysis of those alternatives, not the analysis, but perhaps the mention to those traditional alternatives should be relevant in order to situate what is the point in which your approach in fact provides some new insight, some new possibilities. This is not a criticism, but perhaps a criticism to the presentation of this issue, of these and other issues, that Leonardo said something similar to this. I think that showing the relation to the former approaches would be very relevant in order to allow the appreciation of the specific relevance of your work, that I think is really a work that may achieve relevance in the field. Would you like to say something?
I agree with you. I think in chapter 6 we are presenting many things, but we are not comparing with another approach. And I think I can improve these chapters with what you and Leo totally said.
Yes, and I think that I stimulate you and your advisors to develop those contributions a bit more, because I think they are worthy of being presented, publicated. However, a more precise statement about what are the specific contributions is the issue. Let me go to page 95. Now it's just a curiosity. In the figures in this page, the state feedback control becomes worse than the output feedback control. Is there some reason or is there some error?
The state, this is not an error. But I don't know.
It's really, this is correct. The output feedback becomes better than the state feedback in this case?
Yeah, the results are correct.
Okay, please verify what's the reason. It's very strange.
Can I comment on that really quickly?
Of course.
Yeah.
If you go to the end of page 94, the previous one, 94, you use different weights for state feedback and output feedback. So
yeah.
You use a different gamma one. You use 1,000 for state feedback and 500 for output feedback.
Oh, okay. Yeah. This explains. The figure should contain that explanation.
Yeah, I will include that.
Page 132, 132. Oh, no. Let's, it's a small detail, not relevant. Page 136, 136. I'd like to ask you to explain. It's perhaps what you tried to say in this final paragraph of section 7.3. You say that finally it's worth highlighting that the Chilchuroto UAV achieved better tracking performance in the second experiment in comparison with the first. This is because the controller considers the same tuning for hovering, transition, and cruise flight modes. Therefore, due to the change in the dynamics of the system in each flight mode, there exists a tuning trade-off. I have not understood what is this tuning trade-off.
Okay, in this section of this chapter, we designed a single nonlinear double infinity controller to handle with the full flight envelope of the Chilchuroto UAV.
Yes.
We are dealing using one nonlinear controller with the helicopter flight mode, with the transitioning, and also with the cruise flight mode. And as I explained it, the dynamics of the GTHOTAV change in each flight mode. And in this case, we have a single tuning for all the flight modes. And when the GTHOTAV is operating in the airplane flight mode, it cannot perform huge, aggressive. It's not aggressive.
Okay, understood. You have tuned in the first case only for the flight mode with not helicopter. In the first case.
In this case, I found a tuning that's good for both flights. This tuning works well in the helicopter flight mode and works well in the aircraft flight mode.
Okay.
But there's a trade-off. If I tune very well to operate in the helicopter flight mode, when I go to the airplane flight mode, I can lose performance, and vice versa.
Okay. I think I understood. Perhaps extending the explanation with one or more sentences would turn it easier to track. The next in page 131, let's come back to 131. Leonardo has already commented about this. This figure 713 shows the law which you use to change from one mode to the other mode. You change the availability of the control signals. I think you use or you don't use the control signals related to the plane motion. I think that Leonardo has already commented that this sounds to me a bit non-systematic, a bit heuristic, and perhaps in this case, I think that you should examine the Takagi-Sugino approach. Have you already studied that approach?
I just saw, but I don't know.
The idea of Takagi-Sugino
I know the approach. Yes, I know the idea.
The idea is to in some way to connect the control law that would be used for situations that are too different in the system. So the system is a nonlinear system as in this case, and the nonlinear system requires different control laws. The idea of Takagi-Sugino is to provide a control transition that uses the robustness of the control, uses the robust control law that is valid in the whole range of the transition. In this way, you can provide some guarantees that the stability will hold in during the transition. I think that something like this could solve this issue better than using a heuristic approach. So I think that those are the main questions I have annotated here. I must finish my talk saying that I really liked your work. It's really very interesting. It's you indeed have worked with a large range of subjects, of different subjects. You had to go to the foundations of robust control. You had to search the initial steps of formulation of H2, H infinite controllers in another way, with another kind of norm being optimized. So, and you made that. It's really interesting to see this in your work. You made all those steps with the objective of reaching to a controller that is suitable to control a very hard nonlinear system, nonlinear system that is far from trivial of being controlled. And you achieved a successful control law for that system. It's amazing, and I like this. And so I think that it's quite expectable that you would not, in a single PhD thesis, you would not be expected to present all the details of those developments. So I think that your work is indeed a very good work, and perhaps you could improve some details in the presentation in order to make it a material that can be used by the future students, both by Guilherme or by anyone. So I thank again Guilherme, Sérgio, and Daniel, and I return the speech to Guilherme.
Okay, thank you very much, Ricardo. The points that you raised were very, very precise, and that was Daniel and Sergio were expecting to hear, and I think it improved a lot of the qualities for all of your questions and from the examination board there. So thank you very much for the comments. I make some notes, as I said for the other members. I tried to comment something at the end in my turn. So I'm back. Okay, so now I pass to the last member of the committee. I'd like to thank you so much to Vitor. Vitor was the substitute member of this examination board, and in this week we need to access him, and so thank you a lot to be here. And so Daniel is yours now. So thank you.
Okay, thanks for the invitation, and it's a pleasure to be here. So first of all, I'd like to congratulate you, Daniel, Guilherme, Sergio, because the work is very nice. I really liked it. And I'm going to try to touch on some points, okay, along the text. Many of them, everyone already commented on, so I'm going to try to touch on some different ones, okay?
Okay.
Some are just picuinhas, because eu sou chato. So the first one is just in some points along the text, you write some stuff you could write a little better, not exactly better. So use some terms in place of others. So it's a viscosity solution, not a viscous solution. Okay? É a solução de viscosidade, não uma solução viscosa.
Okay.
Okay? And also
Okay.
the way you write it on the approximate solution part in chapter 2, it seems like they're trying to do something different, but then they just, the methods on finite difference and finite elements, they converge to they try to obtain the viscosity solution, but it's basically the same thing you're doing, right? It's just the viscosity solution is something that's easier to define because you can prove the uniqueness, so you can prove that it converges to it, right? If you try to use a different type of weak solution, you do, okay, I convert to a Lipschitz solution, it could be something different because there are infinite solutions, okay? Okay. So in chapter 3, it's just a style comment, okay? Because throughout your whole text, you use infinite horizon control problems, okay? But when you're driving the Hamilton-Jacob-Bellman equation, the HJB equation, in section 3.3, you use a finite horizon problem.
Yeah.
Okay.
The idea here was to present the control problem.
Yeah, I know. It was just to present the problem in itself, I know. But it's just that reflected in something else along your text, which is something that I don't remember. Someone touched on. I don't remember who now because I'm the last. It's been a lot of hours now. So, and also Kirk's book, the one you're citing, it's from 1978, right? Not 2012.
Well, yeah.
Okay.
Okay.
The thing I wanted to comment on because of the HJB equation is just the HJB equation you reach at the end, 3.29. Right, next page. The other one, yeah, still next page. Yeah, so this Hamilton-Jacob-Bellman equation you reach, or the one up top, 3.27, therefore evolutive equations, they're Hamilton-Jacob evolutive solutions, meaning that they evolve through time. And since you're using a time invariant system and you have an infinite horizon, you always have a stationary solution, okay? So you never have that first term. Your value function never depends on time, which is something that you needed to write somewhere, right? But you never wrote it along your text. Just say, oh, here's our value function is always stationary because of this. So this term is 0. Because in chapter, because first you need this to do the next method you're going to do in section 3.4, right?
Yeah.
To do your successive approximations, you need this to be a stationary value function. Because from what I understood in your method in chapter 4, next chapter, you're basically doing a policy iteration, and you can't do policy iteration for value functions that change in time, okay? That evolve through time. They're simpler to solve, right? So since you're solving it like this, you need that to be true, okay? Okay. Just like an assumption you need to place somewhere. Just, oh, hey, I need this. There is a small line somewhere. Yeah, I think that's that. And then, yeah, I already talked about this. Okay. And that's why I had to talk up to chapter 4. Okay. In chapter 5, I was really confused as well about the disturbance being 0 being the optimal one. But then I think it made sense after you explained to Adrian, right? The thing about the range of the disturbance being the same as the inputs.
The image space.
Yeah, there is no null space, right? The null space is empty, so
Yes, in this case.
yeah, and so I think that even if you tried, okay, so you wouldn't for this specific, how do I say this? In the linear case, or in H2 and H infinity, like noble ones, you wouldn't have the same thing, right? The same solution like you have here, but just because H2 can't exist without bounding something on the control input. If you don't have a cost and the control, because you don't have any bounds, it wouldn't find a solution, but H infinity can. And you don't have this problem with your problems, right? Because you're bounding F dot, because you're bounding X dot, since you're in the sublab space, you don't have this problem. And this is a major advantage you have, right? I think you should like write a remark about this somewhere and say, oh, hey, we have this advantage, right? We don't have to, no, you say that, but you don't sell it as much as you could. Because you say, hey, we don't need to place, you say, we don't place a bound, we don't place a cost in the inputs, but you could, right? If you wanted to, you could like augment the problem and treat it a little different and place it, but you don't have to, right? Which is different from H2, or like just an optimal problem with a quadratic cost function, in which you have to place a cost and a definite cost, a positive definite cost on the inputs. Otherwise, they'll just be infinity since you're not bounding them, right? You don't have like a closed set for the inputs, right? You're just like trying to find the optimum in the whole state space. So that's a really important property you have that you could sell better, right?
Okay.
I think your work is very nice, but you could, as we say in Portuguese, you could vender melhor seu peixe. Você podia vender seu peixe melhor. Okay?
Yeah, I agree.
That's a huge advantage you have, and that also that's also another advantage you have in your W infinity compared to H infinity. Is even if you don't bound the inputs, you don't have one of the huge problems you have with H infinity controllers, or at least for linear systems. I'm not used to H infinity controllers for non-linear systems. But H infinity controllers for linear systems, if you use the optimal controller, they tend to be really high gain controllers. Right? So they say, oh, okay, I want to reject the disturbance the maximum I can. So if you found a case like this one you have, in which, okay, the optimal disturbance is 0 because it doesn't matter, like this one you found, the control gain in H infinity will be 10 to the 6, 10 to the 7. Be something huge, right? Which is probably not the case in your case because you have the weights on the derivative. You have the weights on X dots or Z2 dot, depending on which one you're using, okay?
Okay.
So just sell it better. You have really nice results. You just have to sell them a little bit better, okay?
Okay, I'll try to do that.
Yeah, but I really liked it. I really liked it. Up to chapter 5, it's really, really good. I really liked your text. Okay. And now to chapter 6. So I have, since I'm substituting for Moselli, he also sent me his comments. So I'll talk about his comments now. And then I'll go to mine, to chapter 6. Because basically he said the same thing before. He said he really liked your text before chapter 6. He said that it's been a great improvement from the qualification text from chapters 1 to 5. And he also really liked your chapter 7. He said that your chapter 7 is like a mini thesis inside your thesis, and that you have really nice results as well. But that his main concern is your chapter 6, and I'll agree with him. But mostly, I'll send you what he sent me later, then you can have a look. But I agree with him that my main problems are in chapter 6, but not with your results by themselves, but how you presented them as well. Just like Leo said, and also Ricardo Takahashi said, okay? Maybe you could present them a little better and sell them a little better. But you have some really interesting things here that you could do for the linear case, okay? So in the linear case, at least, in the linear case, for H2 and H infinity, I'm not going to talk about H2 here because you're only doing W infinity in chapter 6, right? So in H infinity for linear systems, we do augment the system, like Takahashi said, right? It's really usual to augment the system either by considering weights, like mixed sensitivity, like we're doing a weighted sensitivity, like Adriano said, in which you place a filter in your output that weights the output on different frequency ranges, in which you're basically saying, hey, I only care if my output is high if it's in this frequency range, right? If it's high in the high frequency range, I don't care, right? Because, yeah, I can't do anything about that. Or you could augment the system, for instance, with a model reference and use the output as the difference between the system and the model reference, for instance. It's also a way we do in H infinity for linear systems. And you could also do both of those for your W infinity. I don't know if weighted sensitivity would make sense because I don't know, right? You could make a comparison. For instance, you have your W infinity, the way you presented it, and you could present a weighted sensitivity H infinity controller, right? Because they're both trying to do the same thing. Because weighted sensitivity is a way to try to place weights in your solution to try and shape the dynamic behavior the way you want it, right? And you do this basically in your approach by placing weights, different weights in both norms, right? So you could do a comparison like this and say that, hey, maybe this makes more sense, right? It's easier to think about, because I think that it's easier to think about the weights in your case than weighted sensitivity, right? Because people say, hey, it makes sense. You construct a filter like this and put it like that. It's really hard to think about it, right? After you've done like 100 of them, say, okay, yeah, it makes sense. You do it like this, right? I think yours could be more intuitive. So you could make that comparison and sell your technique better, right? So, hey, we do it like this. You can say that the LMIs are close. They're going to be similar because they will be similar. It's a linear system, so it's not going to change that much. But the approach is different, right? You could say, hey, here, if I think about doing the weights like this, which is the way I can't simply apply Bryson's rule like you said you did, right? I use 1 over the maximum. I think it will be for the exertion of the derivative, and okay. Whereas in the other one, I have to do some magic numbers. You could do that comparison, right? It will be a nice comparison. Okay? That's just like for stuff you could present better. That one, it would be better if you wrote down, because I didn't wrote down that here. I thought about it as they were talking.
Okay, I'm writing here.
Okay. I'll give you some time to I talk about the next ones. Because the next ones...
You can keep talking while I'm...
Okay. Yeah. The next comments I have are mostly about your LMIs, right? Because this was a general comment. I just think you could present it this way so you could sell it better. Because I think you have some really nice results here. Right? Because you have, oh, I have this different approach, right? It's similar, but it's different. And I have this, and this way it's better, right? And in this way, it's probably different. Right? I have to, okay? But then I have to talk about your LMIs just a little bit. If you go to page 84, it's your first LMI for states, for the state feedback, okay? It's okay, it's right. There's no problem with it. It's just weird. The way you use Schur's complement here, it's a bit weird because you didn't decouple the terms in sigma 2, for instance, right? You could have used a Schur's complement on everything and decouple that d sigma AS and d sigma BR as well. Then you wouldn't have these zeros here.
Can you repeat that? I didn't understand.
You could write the Schur complement differently in a way that your sigma 2 wouldn't have these square terms, which is like these cross product terms. And you wouldn't have the DD term, the square term, in the second diagonal as well.
Okay.
In a way that it's not wrong the way you did, right? It's okay. It's just that it's okay for linear systems, for linear certain systems without uncertainty. But then when you used it like this for the uncertain systems, it's not 100% right. It's not wrong, but you need something in the middle to prove that it's right, and people don't like doing it like that anymore. Okay?
Okay.
Because, okay, let me explain. If you go to if you try to do it like this for the uncertain systems, like you did, okay? You presented the uncertain systems with the disturbance model, but it's basically the same thing you did down there, just simpler for me to explain here. Consider you have an uncertainty in the D matrix, okay? In D and A, for instance. Since you have the product of two uncertain matrices in sigma 2 and in the diagonal of 2, 2, since you have that product, you wouldn't have a single convex summation, right? You have a product of two summations, which needs to be written as two summations. Then you need to have two vertices. Then it wouldn't be simply evaluating it at the vertices like you wrote.
Okay. That's the reason I included the section explaining how to formulate this problem for uncertainty systems.
Yeah, but
I agree with you. That's a problem that I created here. I could use.
Yeah, you could just decouple them from Schur, and it would be simpler, right? You would just use the same one for everyone. Okay?
Okay.
Then if you go down just a little more, you're complicating you went down too much. It was still on the same page. Yeah, just go a little bit above. Yeah, there. You're complicating your stability proof. All you need is 6.8. You don't need to use Barbala's lemma or anything, because 6.8 in this case without the disturbance model implies that when you don't have a disturbance, which is when we check for syntoptic stability, right? We check for syntoptic stability without disturbances. 6.8 implies that if you don't have a disturbance, your Lyapunov function's time derivative is negative definite.
Yeah.
Then you already have asymptotic stability by Lyapunov's theorem. You don't have to use Barbala's lemma.
The idea when I inputting the equation 6.9 here is to extend this stability to the case with this term.
That one is okay, right? It's to say, hey, it's bounded by this. That's L2 stability, right? That's okay. That's no problem. My problem is with the line right after 6.8.
Okay.
Consequently, V dot. So you don't employ Barbala's lemma here, right?
Victor.
Yeah. Okay,
Victor, may I say something?
Sure.
Daniel, actually, I do have a problem with the equation, with the inequality 6.8. It's a technicality, but it's something that is important, I think. It's not that easy to use the limit on the left and on the right-hand side as of operator, because you cannot do that, because think about it. You can even do not have the limit on one of the sides of the inequality, right? And it's not okay to use the limits on both sides. You can see that you reach a contradiction, because right after 6.8, you are saying that the limit as t goes to infinity of the Lyapunov function is 0. But on 6.8, you are saying that the limit will be less than 0. So, and this is happening because you cannot just use the limit like this. So you should do, as Professor Victor is saying, you just start from the inequality, and by using Lyapunov theorem without having to mention Barbala's lemma, you just can prove what you want to prove. Thank you, Victor, and sorry for interrupting.
Yeah, no problem. Yeah. So as Leo said, just drop the limit. Drop the limit as well in 6.8. Okay. And then the analysis on 6.9 is okay. There's no problem. You just integrate both sides, which can be done from Gramon's lemma. Okay.
Okay.
Okay. And then just like as another small detail, it's not wrong, but you need something else to prove it. And it's right in this case just because it's a linear system, right? But you're not proving it the way it is. Because your last line in the proof says, consequently, if no disturbance is activated in the system, the closed loop system is exponentially stable with, and then you place your solution for the linear system, okay? That's true because it's a linear system. And every linear system that is asymptotically stable is also exponentially stable. But your proof is not, you are not proving that in your proof, right? So I just wouldn't say anything about that. It's not wrong because you have a linear system, right? You can like place a small remark afterwards and say, hey, here, because of this, we have this property, right? Or if you want to be if you want to be more correct, right? If you want to be on the safe side, you could try to find the Lyapunov exponent that you're proving from 6.8, right? If you replace the left side with a quadratic thing, and then you use the maximum of p, minimum of sigma, or the other way around, and you manipulate a little, you would find an exponentially stable limit, but it wouldn't be exactly the one from the solution. Okay?
Okay.
You probably something that upper bounds it. So to be on the safe side, just don't say anything about it. You don't need exponential stability for anything in what you're saying. So you could like place a small remark and say, hey, since we're dealing with linear systems, we have exponential stability. And this is true, right? But don't place it on the proof. Okay. And then there's the next section, which is the one I couldn't exactly follow due to time, and neither could Moselli. He sent me his math. He didn't follow some of it as well. Some of the problems are basically, I think you're skipping too many steps in between, and then it's hard to follow. Mostly like when you start proving when you start making the LMI, up there in the top is okay. When you say, hey, we have a dynamic controller, that's fine, that's no problem. The problem is after 6.13, when you start doing the congruence transformations, yeah, so that's a thing, right? That's another point. What you're doing is not exactly a similarity transformation, right? Because similarity transformations we apply on systems. And when we're doing what you're doing on the LMI, and it's only on a part of it, on the quadratic form, we call them congruence transformations. Transformação de congruência. Não é transformação de similaridade, é transformação de congruência.
Ok.
Porque você pode aplicar ela só no X, você não precisa aplicar no X ponto, por exemplo. Não precisa ser em tudo. Similaridade tem que ser em tudo, é mais chato. Yeah, so the thing, that's the main problem here is your similarity transformations. They are a little hard to follow. Did you use any reference on how to do this one? It's just, it's different from the similarity transformations I'm used to.
Those similarity transformations here?
Yeah.
They come from my mind. I was trying to solve this, and this is the similarity.
Okay. It's because there are some standard ones that people use for output feedback, which you could check on Doutorado and Paganini's book, which you cited, for instance.
Regarding the H-Fins controller, right?
Yeah. But
try to use.
Don't do it like that. Don't do it like that. If you want an easier place to check, I'd say check maybe the LMI notes from Ricardo from Unicamp. Or maybe some of his papers. It's just that his class notes are easy to follow in this regard.
Okay.
And usually there are some small things you have to do in the similarity transformation. And then, because, for instance, I'm going to give an example of why I couldn't follow, right? I tried to write it down, but I couldn't. For instance, you appear with W, right? And you say that W is S minus Q to minus 1.
W, where's W here? This
W is right before 618. It's the end of the page. The capital W.
Okay.
Here in 618, you forgot to say that you're making another congruence transformation, right? Because you probably multiplied by identity, W identity on one side and identity, W transpose identity on the other side, right? So you forgot to say that? But one problem is, okay, you did this congruence transformation, fine. But then I couldn't understand how you went from your first LMI is in SIIW, larger than 0, is related to your Lyapunov function, right? To 615, right? That one should be equivalent to 615. I couldn't do that, for instance, with your P-1 and M matrices. I couldn't get to that. So I'm sure that it's right because it worked when you simulated everything. Just you don't have to change the simulated transformations you're using because you got to the result you wanted and you needed. You just need to present the steps done in between so that someone can follow, right? Because you're used to them. You say, hey, I did this, and then they did this, and I got here. But then there are a lot of in-between steps that we can't exactly follow, right? Because they're not exactly, since you said it yourself, you came up with this congruence transformation. They're not exactly standard. So we don't exactly know, hey, here, what does this get to, right? So do the step, especially if this were an article, right, and you had a page limit, a page restriction, then fine. Yeah, okay. Just reduce it if a reviewer asks, and then you present the detailed proof. But since this is your thesis and you can use as much space as you want, you're not gonna spend 20 pages on the proof, right? But you could use some extra space. It's better if you if you show the steps, right? Especially if some other student gets your thesis and want to read it and understand, oh, I want to try and do something like this LMI. What do I do? The way it is now, they can't exactly follow your output feedback one.
Okay.
Okay. Yeah. Okay. This part specifically, I wrote it down, so it's fine. I'll send it to you. You can check it later. And then I have some problem.
Can you also write the notes that you said, notes from Ricardo, Professor Ricardo?
Oh, sure. Yeah. I'll write the link. I was checking them yesterday to see if it was the same, but they're not.
Vitor, can I say something? Because
sure.
Daniel, this presentation will be in YouTube forever, so you can watch again after.
Yeah. That's also true, right? Yeah.
Okay.
I'll place the link here on the PDF, so it's easier for you to check when you're.
Thank you.
See what's better. Yeah. Just a sec. Okay. I wrote the link here. Yeah. Okay, that's fine. It's okay. And then the LMI is one thing, and then we have the same problem here again in this proof, but then this one's a little different. At the end of page 87, you're once again using Barbala's lemma, right? Citing Khalil's book. Then we have a problem here. Not that you don't have the result you want. Actually, you don't have the result you're saying you have, Yeah, there's a problem with everything. Okay, so in 6.25 again, as before, present the equation without the limits. Okay, you have v dot is less than minus that term. Okay.
Okay.
Okay, that's no problem there. And then what I think you're trying to cite here is there's a theorem on Khalil's book. I have the page marked. Just a sec, real quick. Because I have the book here. I think you're trying to cite theorem 8.4 from Khalil, which is not Barbala's lemma, right? Which is something that looks like LaSalle. You're trying to use LaSalle here, basically, but you don't have an invariant system, right? And then I have 2 points for you, right? The first point is you have a linear time invariant system. You could simply use LaSalle here. You don't have to use this theorem, right? So in this case, you say, hey, if we don't have disturbances, we have an autonomous system, and we can simply employ LaSalle's invariance principle. And then we prove that x converges to 0, right? Not x augmented, but x, right? Not the same thing here. Not that the limit of v doesn't necessarily go to 0, but from your results, right? They probably do, but not the same thing. So you could simply use LaSalle here, right?
Okay.
If you don't want to use LaSalle and you say, hey, I have a non-autonomous system, use the theorem from Khalil, theorem 8.4. Or if you want to go the long route, you could use Barbala's lemma, but Barbala's lemma is different from what you're using, right? Barbala's lemma simply say that if I have a signal that's uniformly continuous and if I have a signal that's uniformly continuous and that's L1, right? That's integral is limited, right? Then this signal goes to 0 as time goes to 0. That's everything that Barbala's lemma says, right? Which is not what's written here, right? If you wanted to use Barbala's lemma here, you would have to pick v dots as this signal, and then you'd have to take the derivative of it and prove that it's bounded. Then, because it's bounded, then it's Lipschitz, locally Lipschitz, and then it's uniformly continuous because of that. And then, since it's stable, because you already proved that it's stable, the limit of V infinity exists and it's bounded. And then, because of that, the integral is limited. And then, because of that, the signal goes to 0. And then x and x dot go to 0.
Okay.
Okay? It's a long route if you're trying to use Barbala's lemma, which is something that we use more in adaptive control than regular control. Okay?
Okay.
My opinion is simply drop it and use LaSalle's invariance principle. It's easier and it's direct. You don't have any problem using it here. And I'm going to write it down because I forgot. Okay. And then we have section 6.3. The comments I have are basically the same as before. And also the same as Leo and Takahashi already said, okay?
Okay.
And 6.4 is okay. You're simply using D stability. It's fine. Okay, I have a problem with AK in 6.37 because since I didn't understand it up there, I didn't understand it here.
Yes, this is obtained regarding the transformations that I
Yeah. It's just the problem is I didn't understand the transformations up there, so I didn't understand it here, right? I think it's probably right, but you just have to show the steps a little more, okay?
Okay.
And then in 6.5 is, as I said before, you can do two things. One, you can just change the way you're doing sure up there. Or the second one, if you don't want to change it up there, is if you check it, the cross products you have between two uncertain terms always involve one term from the disturbance. So if you said that D, AD, BD, and CD are constant, they're not uncertain, right? If you say that your uncertainty is only on A and B, you don't have to change anything, right? Should be fine the way it is.
Okay.
If you have uncertainty on the others, you can change the way you're doing Schur's complements for some of them, but for others, you need to use some extra results to show that it's still valid, because this is right, it's not wrong, but you have to do some extra steps to show.
Yeah, but
because you have these products.
In this case, I need uncertainties in the disturbance model and this method.
Okay. Then you have to go up there and use sure, or you simply we have ways to deal with double summations, which is not considering every cross vertex, right? For instance, you would have two indices, I and j, but you wouldn't consider every I and every j, because that would work, but that would be too conservative. Then you have ways to make that less conservative, right? There are a lot of different ones, simple ones, and then ones which are more costly, which tend to be better, right? I can show it to you later, just so we don't take long here, okay?
Okay.
And yeah, that's it. I wrote down the stuff about the... I asked to talk in Takahashi's time when he was talking about your output signals behave better than without with the state feedback ones, because Moselli also wrote down, asked me to ask you about that. But then I wrote down that you use different weights, right, for state and output feedback ones. And then my question is, why did you use different ones?
I don't remember very well now, but I think when I consider this gain here in the optimization problem, it was not feasible. The output was not converging.
Okay.
I think that was the answer.
But then you could have used 500 in both of them. No?
I didn't try that.
Yeah, okay.
I have to try this.
Yeah. It's fine. Yeah. Then I have another doubt, which is in 6.6.2, which is you use the pole placement, you use the D stability in 6.47. Why did you choose a ball? Why didn't you use something simpler like a half plane?
Because the answer is because I had the LMIs of a ball and it was easy to implement, so I use it.
The simpler ones are the ones for the half plane, which is just like add like a minus alpha v someplace. It's the simplest ones. And they ensure exponential stability if you use to the left of a half plane. Right? Yeah, but it's fine. It's fine. It was just a doubt. Like, why did you use a ball, not a half plane? Because we usually use balls for a discrete time system, right? It's fine. And yeah, that's it. That's what I had to talk about. Chapter 6. I really like chapter 7. It's really well written. I wrote down like some small like text mistakes, some stuff which weren't exactly defined, but that's small stuff. Yeah, that's it. Thanks.
Thank you, Vito.
Okay, thank you very much, Victor, for your comments. Yes, I commented you before. You went to the point in chapter 6, and that's great. Thanks a lot for a careful reading about this chapter. It will help us to improve that chapter, and that results a lot. Thank you. Okay, so now I change my room because I need to my side. I need to charge my tab. So now I pass the word to Professor Sergio. But first, I'd like to thank you, Sergio. Thank Sergio for this nice, very, very nice collaboration. I think this is a result of work that you I started some time ago, and with Daniel being conducted and doing very nice work with very nice results. So I just say thank you for that collaboration and to conduct Daniel so well. So that's it. Thank you, and your time, your turn.
Thanks, Guillermo. Hi, everybody. Hi, good afternoon. Thanks a lot to all the members of the review board for accepting the invitation of attending to the defense of Daniel. I would like to start in no other way than actually congratulating Daniel for the work that he has conducted over the last years. The presentation was a really good presentation. It has improved a lot from the first presentation that he made us a week ago, and actually has presented the main aspects of the work he's conducted, but obviously not all the aspects, because it's difficult to do so in those 50 minutes. But I think he has done a great job. I would like to also thank Guillermo and Daniel for calling me back some years ago and considering me for trying to help them in guiding Daniel on this work. And I think there's going to be this is just the beginning of a lot of many talk that we will have, not only up to this point, but actually beyond this point, where this is basically just starting a lot of collaborations. I'd like to thank all the comments of the tribunal, starting from Professor Manolo and following from Professor Adriano, Professor Ricardo, Professor Leonardo, and Victor, because they all have recognized, the importance of or the novelty of the work presented by Daniel, which I think it's quite interesting, something that we have talked with Guillermo a lot of times. But it's important, all the comments related that despite that the work can actually be a substantial contribution towards the area of control, it is really important to polish a lot of small details that all of you have pointed out, and that we're going to try to guide Daniel, because we think that all the comments are in the right directions, that we need to make Daniel to emphasize, and especially something that is important is to sell the contribution that he has done. So we really thank for all the comments that you have done, and I think that we're going to try to help Daniel to make sure that all of them are somehow represented in the final manuscript. Related just going to say a little thing about the manuscript in general related to the chapter 7. It's, as I do agree with Professor Victor, which also was one of the comments of Professor Mozzelli, which it's kind of like a mini thesis within the thesis, and I which is in the same direction on the comments from Professor Manolo Hill and Professor Adriano and Professor Leonardo, which they pointed out that it was kind of like offside. Then Guillermo will talk a little bit more about the reason, some of the reasons behind that chapter. But I would like to point out that there's a lot of more in that chapter that actually probably what he has basically expressed in the presentation, but it's in the annex. It's expressed in the annex, and despite that, in the annex is described all the dynamics and the complexity of the problem, which was basically one of the main objectives, being able to control something as complex, which is a completely open field, which is a tilt rotor in the transition phase, which is something that Daniel has been able to accomplish in the simulators, and we're eager and looking forward for hopefully in the next 6 months, or probably more realistic, probably in the next year, to start testing and implementing Daniel's control strategies in the real prototype, which will be manufacturing at the same time, both in Belo Horizonte and in Seville. So it's important, because in order to be able, one of the ideas that we had is, in order to be able to test complex strategies, it was really important for Daniel to develop the whole formulation of a tilt rotor without making simplification. So that's a hard work that Daniel spent so many hours, which have been reflected in some of the papers that are still yet to come related to the modeling. And I do want to make emphasis that it's important. It is true that we're going to try to see if to be consistent with the philosophy of the whole thesis, if we need to reorganize things and probably move those important things towards an annex and focus in the thesis in the things related to the control. And so we'll try to see what's the best way to adapt all the comments related that might look like something that it's not right there, but it was something that it's really important for Daniel. So we'll figure out a way, and I'm sure there will be del gusto. I don't know how to say del gusto of everyone. The final result. It is true that and all the things, the comments that came out, is that, which I think is probably something that we all have heard when we were there at the same situation than Neil, that we don't sell, or we didn't sell properly the things that we accomplished on our PhDs. And I think that that's something that we need to try to help Daniel, because it's our duty as advisors, as Guillermo's and I, to try to let him know, let him see, and especially let him represent those contributions in the thesis, so that actually he is aware of what he has done, and he won't be aware of his done until some time passes by. And as everybody have you said, if the final manuscript becomes something that the students can relate to, and that implies extending some of the explanation so everybody can follow, that's when he's gonna realize that he has done the contribution that I think you all have seen. I mean, we thought that he made a contribution, but it's something that it's difficult to be objective, because it's like our son. So having those comments from your side, that despite the things that need to be improved in the writing and in the explanation, it help us to show Daniel that, you know, he has done something that it can actually be important, but it needs to be polished. So I'd like to thank all the comments, because believe us, that is something, all those comments are something that are going to help us to guide and do the final polishing on the thesis, Daniel, so we can have a really great document, which we have a really great work. We have a great thesis, but it can be improved. So thanks to all the reviewers, to all the members of the tribunal, and thanks, Daniel, for all these years of letting us guide you and congratulate you on the work. And thanks, Guillermo, for thinking in me here to try to help you towards this year. So I have no related comments to the technical parts and the thesis. I think that all of the members of the journal have give a lot of comments that I'm sure that we're going to be eager to starting tomorrow to help Daniel to plasmar my English, plasmar all those ideas in the final document. So thank you everybody, and thanks Daniel, and congratulations.
Thank you, sir.
Okay, thank you very much, Sergio. Now I need to talk something. So I'd like to thank for all the members. I already said before. I think all the comments and all the details that you pointed out were very, very interesting, and most of them touched in the point. So I mean, we caught the main problems that we need to solve. Also, so about Sergio, I said I commented before. I'd like to thank and congratulate Daniel for this nice work. He makes self-confident in this topic, and I think that is very good. That make a PhD student a real doctor, and so I'm happy with that achievement. I have just some comments. As Sergio said before, all the theses born around two things. Around the formulation of the 18th finite controller using rates, using the rate of the cost variable. This is one comment that I received some time ago from my thesis. And the other side is around the tutor review. That Daniel, we start to work with the tutor in his master thesis. I worked before with Sergio. And so all the theoretical part was about how to solve the 18th finite control, the nonlinear 18th finite control, considering the rates of the cost variable, and to solve the problem of the tutor, but mainly between the transition continuously from the helicopter and to the cruise flight mode. So if you remember, in the qualifying exam, all the text was how to solve the problem for the tutor. But some comments said, here you have some examples about two segways, about quadrotors, about tutorotors as well. So this is more a control theory thesis applied for a lot of kind of system, but with some specific problem that is the tutor. So we modified, following this suggestion, the whole structure of the thesis, focusing only on the control theory. But since there is a root part evolving the tutor, we consider as a case study. But it's true that we could try to put this application, for example, into the chapters 5 and 6, only with some numerical examples. But for example, in the modeling, in the model of the tutor, there is a very, very nice contribution, because there is no dynamic model. Yes, it's a mechanical exercise to do that model, but there is no model in that way that is a multi-board dynamic model that takes into account a continuous model of the coefficients. So I don't know, there is some noise here. I don't know if it's from Daniel or... thank you, Daniel. So only the model is a very nice contribution for the aerospace systems and the people that is working with this kind of convertible airplanes. Now we are looking for urban air mobility that is using this kind of multicopters that can take off and land in vertically and can fly faster than helicopters. This is Doutorado is one of these kind of configurations. So the whole thesis is pursuing to solve problems that the Doutorado put to us, but using the robust control for nonlinear systems formulated in the sublab space. So this is the structure. And why the linear? Yes, the linear is a little bit, the linear controller is a little bit strange here, but also following a suggestion in the qualifying that was why you don't formulate this controller for linear systems using LMI. So Daniel tried to solve that. It's not our expertise. I usually work with nonlinear systems, and also LMI for me is just a tool. It's not a field of research. So we try to enter in this adventure, and I don't know. I like the results. Maybe some naive results, but I said before to Victor, please take care of this chapter. I need to improve. For me, it's a little bit naive, but I don't know. I like that. But I think there is very nice contributions as well in that chapter. For example, Professor Ricardo, Leonardo, Professor Victor said that, yes, you can assume a cost variable as the output and the time derivative of the output. But if you put this cost variable into the cost functional, this is in the sublab space. That is not in the Lebesgue space. Okay, because the sublab is a subspace of the Lebesgue space. So if you do that transformation and assume the time derivative of the cost variable, and the time derivative of the cost variable is augmented space, that is assuming the dynamics into the cost function. This is the sublab space. So it's a little bit, I don't know how to say it. I think it's wrong, but it's more fair. It's fairer to consider the sublab space instead only the Lebesgue space. This is the main reason about the structure and why to consider that. I liked about the worst case of disturbance for the particular system of mechanical system where the image is per the same space. But I prefer to explain from the min-max optimization problem, because the saddle point of this min-max optimization point is zero. It's not zero, it's U star and zero. So zero is the saddle point. All the other points are not in the saddle point for the disturbance, no? So it's just related to this kind of nonlinear system, because in the chapter 4, the worst case is just a function, as well for the linear case. So I think in that direction you can try to explain, and also using the idea of the images of the inputs and the disturbance, but that is the saddle point. It's very weird to say, okay, the null disturbance is the worst case. Yeah, for that case, it is the saddle point. It's one part of the saddle point. And just more some comments that I make some notes here. but as a sorry, I'm so happy with all the comments. I think it will improve a lot the thesis. And Adriano commented about the tuning. The tuning is a trick. It's a very tricky problem here, because it's like it's a trade-off. For example, for all the variables that is not involving the control input, it's like the weighting the energy of the states and the variables related to the state directly. And so if you increase the weight of these variables, we increase the energy. And in the other side, if you increase the weight of the dynamics of the system that is taking into account the control input, if you increase, you decrease the energy, because there is a trade-off between these variables. So it's interesting. Here you use the Bryson method, and after the try and error tune, but that's it. Okay, and Professor Ricardo and after Professor Vitor talked about Takai Suheiman. I think this is the main reason that in chapter 7 you present some linear results with the tutor. Why? Because in the master thesis from the Daniel master thesis, we use a kind of adaptive control that is called adaptive mixing control, that tries separating several subsets, the whole space, the whole state space, and we mix it using bump functions, the controllers designed for each subspace. And there you used 82, 8 infinite controllers to design the controllers in each subset. The idea here was to use the same or quite similar adaptive mixing control, but with the linear controllers designed in the sublab space. But for these tutorators, it's not so easy as the previous one. So we need to think in other ways to represent the LPV model or the nonlinear model using another kind of quasi-LPV representations, and redesign all these. But it's quite similar. The adaptive mix control and the formulation Takai Suheiman, it's the philosophy of both controllers are quite similar. And so that is some comments that I liked a lot. The comments I needed to talk about them. So after that, I want to say thank you for all the explanation board, and thank you to Daniel and Sergio for this very nice collaboration, and congratulate Daniel for this nice work. So normally in loco, I pass the word to the audience, but here I will ask Daniel to leave this room, and after the comment talk about if you will be approved or not, I will send a message to you and you enter again. Okay?
Okay.
Okay. Okay. Bye. Thank you. Leonardo, bem. Luciano, desculpa. Eu li Leonardo. Okay, Daniel. After a very hard discussion here and different opinions, so we make a consensus of all the people in the same with the same opinion. So it's not a consensus. So congratulations. Now you are a doctor. You are approved. So congratulations. So.
Congratulations.
So I don't know if you want to say something.
It's mute. Daniel, it's mute.
Oh, no. Okay, I was talking. I would like to thank the committee for accepting the invitation and for all the comments in the work. I will try to include all the comments in the thesis, and I think all the comments were good comments and will improve a lot the manuscript. And all the comments also helped me to develop this version now. I know it's not so good as it should be, but I'll try to make a good version for the final manuscript. Thank you all.
Okay, thank you, Daniel. So
Congratulations, Daniel.
Thank you.
Parabéns, Daniel.
Parabéns, Daniel.
Parabéns,
Thank you.
Daniel.
Thank you.
Parabéns. I don't know how is now in Seville, but in Spain, after the PhD committee, the PhD candidate, after approved, he conducted all the committee to a restaurant and pay a very nice lunch or dinner. And so, but now with the pandemic,
That's a very nice custom here.
yeah, so,
We'll go over there. Don't worry. We'll go over there.
Daniel, nos debes una.
Okay, so I don't know. I would like to say thank you to Daniel because I think this is about 7 years because it's 4 years and a half of PhD and 3 years and a half of master. So 7 years. Oh, wow, that's it's a game of patience of both sides. I know I'm not easy. But congratulations, Neri. You did a very nice work from the control theory, from the airspace area. So it's a very, very solid and nice work. Congratulations.
And I also would like to thank you and Sergio, and I hope you have more patience to work with me in the years that will come.
Yeah. I learned to have patience too, but I know that I'm more complicated than you, so it's good. It's good. From some chalks born a nice words, so that's good. Yeah, Daniel, you try to make a postdoc. I don't know if here or with Sergio, but at first he starts here, and you will follow some scholarship. That's important. And so, okay, so I don't know if someone wants to say something.
I just want to thank you all for this work. It was really nice to work with you in this tribunal, right? So that's the first time. In Spanish, tribunal, it's an interesting word because in Brazil, in Portuguese, tribunal means like a jury in a legal system.
Criminal jury, yes.
Criminal jury. So
Aquí también.
first time I am in the tribunal.
In Spanish is the same. It's for criminal or for.
Okay. So thank you very much.
So,
Thank you.
thank you.
Okay, bye.
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 Parabéns.
Bye.
Now, Daniel.
Bye bye. Thank you all.